I hope you enjoyed yesterday's session. All right, so the recording just started. For all the speakers in this session, just a reminder, your talks before the break are 20 minutes, including questions. I'm going to give you a 5-minute warning. So after 15 minutes of your talk, and then when 3 minutes are left, I'll give you a second warning, so you should wrap up. And if there's time for questions, we'll use that last couple minutes for questions. And if there is no time, questions can be posted on the Slack channel. So let's see. So it's 4 p.m. already. We're going to start with the first speaker of the afternoon. We will continue with the direct detection talks from yesterday. And the first speaker is Francesco Nuti. Francesco, whenever you're ready, you can share the screen. If you
Hi,
can.
thank you. Thank you for giving me this opportunity. I'll try to share my screen. I tried to upload my slide, but I wasn't successful. I'll try again after my talk. Okay, I'll share my screen and you let me know if you can see it.
Yes, that works.
Okay. No, sorry. Can you see it in full screen?
Yes.
Yes, yes.
Okay. Okay. Thank you very much for giving me this opportunity to present at this conference. My name is Francesco Nuti of the University of Melbourne, and today I will talk about the Saber South experiment at the Stoll Underground Physics Laboratory. Saber is a sodium iodide with active background rejection experiment, and the goal of Saber are to perform a model-independent verification and exclusion of the long-lasting Gamma Libra annual modulation, and perform direct detection searches of dark matter, as well as other physics measurements that can be done with a low background detector, for instance, some quantum mechanics tests. The focus of this kind of experiment, compared to the others currently running, is achieving a very low background, below 1 count per day per kilogram per kiloelectron volt. Sorry. Saber consists of 2 experiments. One is located at the Grand Sasso National Laboratory in the Northern Hemisphere, and the other one, Saber South, will be installed at the Stoll Underground Physics Laboratory in the Southern Hemisphere. The dual location allow to reject any local seasonal background which might have a modulation, and so will affect any measurement of annual modulation. This talk focuses on Saber South. So the Saber South group is composed of 46 members and across 5 institutions. These are the main Australian universities and the ANSTO, that is the Australian Nuclear Research and Technology Organization. The Stoll Underground Physics Laboratory is the first underground physics laboratory that will be built in the Southern Hemisphere, and it's located at the Stoll Gold Mine, 240 meters northwest from Melbourne. And here in this picture, you can see a schematic of the decline of the mine, and the SAPO laboratory is in construction at 1,025 meters under the surface, and this is approximately 2,900 kilometer water equivalent of shielding from cosmic rays. Here is a plant of the SAPOL laboratory. The main experimental hall is 10 meters wide by 30 meters long and has a minimum height of 12 meters. It's operated as a radon suppressed clean room. The Sabre South experiment will be placed here in the main hall as the first experiment in this laboratory, and there are going to be also rooms dedicated to high purity germanium detectors. The access is through this part of the laboratory for pedestrians, and there is a loading bay for to bring to the laboratory bulky items. The construction of the project has been financed by the state government of Victoria and the Australian government with 10 million Australian dollars, and the excavation has been completed in June. The area has been shotcreted, and then the walls have been coated with the tech flex to reduce radon penetration. The material used in the construction of the laboratory are all meticulously screened for radioactivity with the sodium iodide detectors and high purity germanium detectors. The expected completion of the laboratory is December 2021. And soon afterwards, the Sabre South commissioning should be starting and expected to be completed in early 2022. Here are the most recent pictures of the SAPOL laboratory. As you can see, a lot of services and the structures of the germanium room are all in place. Once the construction is completed, the first we will perform initial background measurements using muon detectors, gamma spectrometers, and neutron detector to assess the background, to characterize the background of the laboratory. So moving to Sabre South, so as I said, the experiment focuses on achieving a very low background for a sodium iodide experiment, and also being able to detect energies as low as possible. So the detector, at the core of the detector are the sodium iodide crystal units, which are immersed in a liquid scintillator vessel, and this is shielded then from external radiation with an external shielding made of steel and polyethylene. And there is also muon detector panels. There are also muon detector panels at the top to shield against cosmogenic muons. So the detector units are designed with the intent of having the minimum material so that on one side the radiation from expected from this material is minimized, and on the other hand you also have maximum probability for radiation to be either detected in the crystal detector or in the surrounding liquid scintillator. Each enclosure can host a sodium iodide detector of up to 7 kilograms in mass, and is coupled directly to 3 inches Mamatsu PMTs with high quantum efficiency. The components of the enclosure are high purity copper and Teflon to minimize the amount of radiation emitted by those components. So we have a 5 kilogram test crystal for Saber South that was produced by RMD in Boston using the vertical Bridgman method. This crystal has been shipped to LNGS and is currently in preparation for testing. There has been some ICP-MS measurement done on offcuts of this crystal, which show contamination of potassium in the tip of 5 ppb and in the bulk of less than 10 ppb. RMD has also previously grown a 3.4 kilogram crystal for Saber called NA33, and for this crystal the characterization has been already done, and as you can see from this table comparison, it has compatible light yields to other experiments and lower potassium and lower potassium contamination. The alpha rate, mostly from polonium-210, are slightly lower than Hannes cosine, but not at the level of DAM at the moment. So we also aim to measure, to do measurements of sodium quenching factors on the crystal that we are going to use for Saber South. So we have developed a measurement of quenching factor using the Heavy Ion Accelerator facility in Canberra, Australia. And we have worked on using
I think we lost you, Francesco. I don't know if you can hear us, but if so, please try to reconnect or reset your connection. Your mouse is moving.
Hello, can you hear me?
Yes.
Sorry, I don't know what happened. I'll share again my screen. I hope it doesn't happen. It doesn't happen again. Did you?
Yeah, that's where you were.
Using a mock-up, as you can see in this picture. Also, the crystal insertion extraction system has been developed in collaboration with the NFN ROM, and this requires the use of a glove box that to be installed on top of the vessel once the top part of the shielding is removed. And this has also been produced by Palazzo SRL in Italy, and the validation tests are due to be completed by the end of this month. The crystals are inserted inside this a steel vessel, which was produced in Australia by Tasweld with very low background still. And it's going to be filled with 12,000 liters of linear alkyl benzene doped with PPO and bis MSB. The base scintillator material comes from Nanjing via the Juno collaboration, and it has properties compatible for this kind of experiment. The scintillator has been already sent to Melbourne. The signal in the liquid scintillator are picked up with 18 Hamamatsu R5912 PMTs with the oil-proof base. So the whole unit is going to be immersed in the liquid scintillator. And the system is designed to pick up any deposit of energy above 100 kiloelectron volts, and we expect an 85% reduction of backgrounds due to internal contamination of potassium-40 in the crystals.
Sorry, it's 15 minutes, you have 5 minutes left.
Okay, yeah, thanks. So we have in place a facility in order to characterize the properties of the PMTs that we are going to use in the experiment. We are capable through a laser pulse to being able to measure a single photon electron response, absolute quantum efficiency, as well as dark rate as function of voltage and temperature and timing of the pulses. Here on the right, you can see the model that we are developing of a single photoelectron charge. Finally, the muon Vito system is going to a series of plastic scintillator of type AJ200 placed on top of the vessel, which will be used for tagging muon. We can have also some spatial reconstruction from here using the timing between the pulses recorded at the two ends of the plastic scintillators. The acquisition is managed by online system. Each detector has a separate digitizer, but they have a unique clock, and there is an external trigger board that applies the logic to trigger the event. Because we are looking for modulations, we need to also to take into consideration any fluctuation in the parameter of the experiment. So we have a monitoring system to basically monitor high voltage of PMTs, temperature, humidity, radon level, and the vibration, since this is still an active mine. Finally, we have estimated the projected sensitivity for Saber South for a DAMA-like annual modulation, assuming 50 kilograms of crystal target mass, and we expect to be able to discover the signal with 5 sigma in 2 years and exclude that 5 sigma in 5 years. Here is a comparison of the projected sensitivity to discovery of Saber, Anais, and cosine. Here, I just want to say that we can, because of the lower background, we will be capable of producing result at the time compatible with the Anais and cosine, despite starting the acquisition later. So to conclude, Yeah, I'm just concluding. So Sapphire construction is ongoing and expected to be finished by the end of the year. And then Saber South will be hosted at Sapphire and will start running in early 2022. We expect to provide results on the gamma-like modulation within a few years from its beginning. Thank you very much for the attention.
Thank you, Francesco. Very nice talk. We have time for one quick question. Somebody has a question, please raise your hand. There is one raised. Give me 1 sec. And that's Teresa. Please go ahead.
Yes, I have a question regarding the schedule of South and North. Do you plan that both experiments will kind of start simultaneously taking data? Because the plot you showed before, I guess this was for Sabre South alone, no? In the slide before.
Yes, so I can't comment, to be honest, too much about the expected start date of Sabre North. I know that things are moving and there is optimism on when the Sabre North experiment will start, but I can't comment, unfortunately, on when if it will be able to start the same time of Sabre South.
Okay, thank you.
Thank you. Thank you, Francesco, again. Any other questions, please, you can post them in the Slack channel. So let's move to the next speaker, which is Maria Martinez. Maria, whenever you're ready, you can share.
Okay, thank you. You can see my screen?
Yes, go ahead.
Okay. So first of all, thank you to the organizers for this opportunity to present you the results of ANAIS 112. So yeah, as the previous speaker, we continue talking about annual modulation. So we expect this annual modulation in the dark matter interaction rate due to the movement of the Earth around the sun. And in fact, the Gamma Libra experiment has measured this signal for more than 20 years. Here I present you an update of the Gamma Libra results presented in the EPS conference this summer, where they released 2 more cycles of their data. So now Gamma signal claim reached a confidence level of more than 13 sigma, and they have also lowered his energy threshold, so adding 1 more point at 0.75 kilo electron volts. The problem, as you know, this signal is not compatible with the negative result of other experiments, but the comparison is model dependent. So we need this model independent confirmation using the same target. This is the scope of many experiments around the world, as we have already heard about Sabre South experiment. 2 of them are taking data now, are cosine 100 in Korea and ANAIS 112 in Spain. That's the experiment that I'm presenting now. So the goal of ANAIS 112 is, as I said, give an independent confirmation of the Gamma Libra modulation signal using the same target and the same technique, but some different experimental approach and environmental conditions. So the experiment is at the Canfrant Underground Laboratory in the Spanish Pyrenees. And here you can see our detector. It's composed of 9 sodium iodine scintillators. Each scintillator is 12.5 kilograms in mass and is coupled with 2 high quantum efficiency photomultipliers. This is one nice point of our experiment, that we have an excellent light yield of 15 photoelectrons per keV. So it allows us to reach a very low energy threshold. The experiment is surrounded with the usual threshold, with the usual shieldings. We have also, contrary to Gamma Libra, we have a muon veto with 16 plastic scintillators surrounding the experiment. And the experiment is taking data in Canfrance since August 2017. So we have accumulated more than 400 kilograms of exposure right now. Very interesting point of our experiment is the low energy calibration. So our crystals are equipped with a Mylar window, very thin window that allow us to calibrate the detectors with low energy gamma rays. We are calibrating with these energies down to the region of interest, that is from 1 to 6 kiloelectron volts. And we are performing this calibration every 2 weeks. So on the one hand, we can control the stability of the experiment and correct the small variation in gain of our detectors. On the other hand, we have calibration line as very low energy. And for our low energy calibration, we use them in combination with 2 internal lines coming from 2 internal contaminants that are sodium-22 and potassium-40. These 2 contaminants decay by electron capture, so we can measure the atomic excitation in one crystal that produce a peak of 0.9 keV in the case of sodium-22 or 3.2 kiloelectron volts in the case of potassium-40, and we can tag this decay with the high energy gamma that it produces and goes to another of the crystals. So we have these 2 populations very well characterized. In particular, the sodium-22 population that is produced this peak just below our region of interest. It agrees with the estimation of the amount of this contaminant, so we can say that effectively we are triggering with high efficiency below 1 kilo. Here you can see also the residuals of our energy calibration. In particular, in the region of interest, we have negligible residuals. Okay, concerning our event selection. So our background is dominated by non-bulk scintillation events, so events that are not coming from the crystal itself. So our strategy, we have follow a blinded analysis. Multiplicity 1 events in the region of interest are blind, and we use for our cuts selection and efficiency calculation the calibration events and these 2 population of events, multiplicity 2 events coming from potassium-40 and sodium-22. These are the cuts that we are applying to our data in order to reject these non-bulk scintillation events. Most of them are coming from events that are very fast, compatible with Cherenkov light producing the photomultipliers. These are very easy to select due to the very different pulse timing characteristic with respect to sodium iodine scintillator events. We are cutting them with this biparametric cut. You can see here the effect of this cut. This is the magenta line. So I remember you, this is our raw background spectrum, the black line. Then we are also applying a cut to filter asymmetric events that have also origin in the photomultipliers. These events are concentrated mainly in the very low energy region, so below 2 kiloelectron volts. And then we are also removing 1 second after every muon passage a multiplicity 1. In total, this is our efficiency corrected background, the blue line here. And in the upper panel, you can see our efficiency. So you can see that we have very high efficiency down to 2 kiloelectron volts, around larger than 90% for all the crystals. And then it decreases mainly due to this asymmetric cut, up to reaching something around 20% at 1 kilo. Okay, regarding our background model, we have measured all the possible contaminants in our experiment and perform a Monte Carlo simulation of our experiment that agrees quite well, as you can see here. The green line is the Monte Carlo simulation and blue is the data, except in the very low energy region. So below 2 kiloelectron volts, we have an excess with respect to our Monte Carlo model. So it can be due to some element that we are not including correctly in our Monte Carlo model, or noise that no scintillation event that are leaking or filtering protocols. Anyway, this Monte Carlo model reproduces very well the time behavior of our background. Here you can see our model in green compared with our data as a function of data taking time for events not blinded population. So multiplicity 1 events outside the region of interest, and multiplicity 2 events in the region of interest. Okay, now moving to our annual modulation analysis, we focus on a model-independent analysis, searching for a modulation. In order to compare with gamma, we look in the same regions as gamma, so from 1 to 6 kiloelectron volt and from 2 to 6 kiloelectron volt. And we also fix the period of the modulation to 1 year and the phase to the second year. Here you can see also the exposure in which we have performed this analysis. So corresponding to 3 years of data taking. You can see here also that our lifetime is very, very good. We are measuring 90%, 95% of the time. Okay, so we performed chi-square minimization over of data, but as I said before, our background is decreasing. In order to don't have systematic effects coming from this decreasing background, we perform the fit directly on the data, not on the residuals, but directly on the data. And for this, we have to introduce also a model for our decreasing background. So a model for the decreasing background plus the modulation term. For the decreasing background, we have tried 2 approaches. First of all, just assume an exponential decay. This was the approach we follow in the first publication with 1.5 years. In this case, you have three parameters related to the background plus the modulation amplitude. The second approach is to use directly our Monte Carlo simulation that we convert into a PDF, and then we reduce the number of free parameters related to the background to 2. Okay, so here I present you the results with these 2 models, model 1 in the upper panels, model 2 in the lower panels, and in the 2 regions of interest. So as you can see, the null hypothesis is well supported by the data. And for the modulation hypothesis, we obtain modulations compatible with 0. Here I show you also the same, but including also the gamma libra modulation in the result. As you can see in the p-values, the gamma libra hypothesis is less favored by our data. Here in the lower panel, you can see the same, but in the residual, so you can see appreciate the difference. Okay, we have followed a third approach in modeling our data, that is modeling separately the background for every detector. So our Monte Carlo simulation for every detector. In this case, we have 19 free parameters plus the modulation amplitude. Again, as you can see, the null hypothesis is well supported by the data. Here we can see how the individual p-values in the case of region 1 to 6 are very good for all detectors except for 2 of them. So it seems that, as I've mentioned before, when I was talking about the background model, it seems that there are some noise events or no bulk scintillation events that are leaking our filtering protocol. So I will talk at the end of the work that we are doing in improving our filtering in this region. So now let me summarize our result, the 3-year results of analysis 112. Here in this table, you have the summary of the previous slides. So all of them are producing compatible results. In all the cases, the data supports the null hypothesis with lower p-value in the case of 1 to 6, as I've already mentioned. And for the modulation hypothesis, we obtain in all cases best fit modulation compatible with 0 at 1 sigma. And the standard deviation of the modulation amplitude in the last case, when we separate the description of every detector. It provides a better description of all data and reduce the standard modulation, the standard deviation of the modulation amplitude. So is this result that we use to release or final result that you can see here in this plot. So the points are the results of Anais with the 1 sigma standard, with the 1 standard deviation of the fit. And in blue, you have the Gamma Libra modulation results for 1 to 6 kiloelectron volts and for 2 to 6 kiloelectron volts. So as you can see, our best fits now are incompatible with Gamma Libra at 3.3 or 2.6 sigma, depending on the energy region. And the bands are or current sensitivity, 1 sigma, 2 sigma, 3 sigma bands. So as you can see also here, our current sensitivity to the Gamma Libra results are 2.5 sigma in the 1 to 6 kiloelectron volt region and 2.7 sigma in the 2 to 6 kiloelectron volt region. We have also performed some consistency checks, and in particular, we have checked that our fit has no bias. We have performed this check with Monte Carlo simulations. And we have also performed a frequency analysis, and we have not found any statistically significant modulation at any frequency. We have also performed a phase-free analysis. So in this case, we have left free both the modulation amplitude and the phase. In this case here, you have the result for the 3 models and the 2 energy regions. The points are the the Anais results compared with the crosses that are Gamma results. But in this case, this fit is biased. We have checked it as you can expect because of the nonlinearity in the parameters. We have checked it and compute the expected bias that is proportional to the standard deviation. So if we take into account this bias, our results are still compatible with the absence of modulation at 1 sigma. Okay, now
5 minutes, Maria.
Okay, thank you. Let me talk about our expected sensitivity. We have calculated it before the analysis of the annual modulation based on our first estimation of our background and efficiency. And we have also checked that this calculation were correct with the data. Here you can see the 3 data releases up to now of Anais 112 with 1.5 years, 2 years and 3 years that perfectly agrees with our estimation. So our present sensitivity with 3 years of data taking, as I said, is around 2.5 sigma, and we expect to go beyond 3 sigma sensitivity with the 5 years of data taking that are scheduled for the Anais experiment. Okay, just some brief words about this work that we are doing in improving our filter protocols. We are working with machine learning techniques, in particular with a 2-phase boosted decision tree, and we already have some preliminary results that I will show you here. So with this method, we are able to clean our background in the very low energy region. That is where this we are suspecting that some events were leaking or filtering protocols. Here you can see how, keeping the same efficiency, we are obtaining 26% background reduction in this energy region. When we perform the annual modulation with these new filtering protocols, that still are compatible with the absence of modulation in all the studied scenarios. In particular, you can see how now we obtain better Q values for in the 1 to 6 kiloelectron volt region. And we have also done updating our sensitivity. Thanks to this background reduction, our sensitivity will increase a little in the scheduled time of Anais. Okay, just to finish my talk, let me open this question is when this is real model independent test of the Dama Libra result. Of course, if you are using the same target material, the comparison is direct in electron recoil energy. But if the signal, dark matter signal goes to the nuclear recoil, to a nuclear recoil channel, then we have to correct by the quenching factor. This energy is quenched respect to the energy of the electron recoils, that is where in the channel where we are calibrating our experiments. So we have to measure this quenching factor and correct. So the response of different detectors to dark matter particles interacting with nucleus could differ if the quenching factor is different. And in fact, this is the experimental situation now. We have many quenching factor measurements, in particular for sodium, where the quenching decrease when the energy decrease. And this contrasts with the Dama Libra reported value that is constant with energy at a higher value. So this is an important point in order to give really a model independent test of Dama Libra. This spread in quenching factor measurement is point to dependence on crystal properties or is due to systematic in the measurement. So to answer this question, we have performed a combined measurements with the different crystals together with some cosine groups. I can present you some very preliminary results that were presented in talk last week, 2 weeks ago, in which we are obtaining for all the crystal measurements, measure 5 crystals, 5 different crystals were obtaining same quenching values that are constant in energy when we calibrate with energy lines in the region of interest. When we use for the calibration only one line, that is very common in many of these quenching factor experiments, due to the nonlinearities in the response of the crystal, we obtain quenching that decrease with the energy. But this is an artifact due to the nonlinearity of the response of the crystal. So these results are preliminary and we expect to present them very soon. So, okay, this brings me just to my conclusions. So Anais is taking in data for 4 years now. And with these three years that I've presented you, we are compatible with the absence of modulation and incompatible with Dama Libra with a sensitivity that is 2.5 sigma, 2.7 sigma. Okay, I think I can stop here. Thank you and wait for the questions.
Thank you, Maria. We have time for, again, one very quick question, if there is any. Otherwise, you can ask for questions later in Slack. Let me see. If you have a question, this is the time to raise your hand.
Oh, sorry.
All right. Well, thanks, Maria, again. Let's move to the next speaker. It's Andrea Messina. Andrea,
yes.
Whenever you're ready, you can share your video. Okay, that works.
So you should see full screen now. Can you? Yes,
perfect.
Okay, so first of all, I would like to thank the organizers for the opportunity to present the CSIC experiment. I'm here on behalf of the collaboration. The CSIC collaboration is a relatively young collaboration. However, already encloses 50 people from 8 different institutions in 4 countries. So the aim of the CSIC project is to develop a large detector for precision 3D tracking of low energy nuclear recoils as those produced by dark matter interaction. This is, as we have seen, a very challenging experimental environment because the background, well, the signal is very low. The background rate is high, and so we need to carefully reject the background. And on top of this, the energy released in the detector is small, and thus we have to look for low threshold devices. Our idea is to develop a strategy to be able to photograph nuclear recoils, and we want to do that in the collision between with light elements, as those here. So basically helium, which is a very light element, and we want to do that in a gaseous environment, such to be able to see the tiny tracklet of the nuclear recoils. Our goal is to develop a TPC because we want to read out a large area detector, such to have a relatively large mass, since we have a gaseous detector, and the amplification stage will be provided by 3 gems, and in the amplification light is produced. And this is the light read out by scientific CMOS camera and photomultipliers. In this way, we can really take pictures of events. Here you see 2 different pictures of a nuclear and an electron recoil, and this allows us to also have a 3D reconstruction, a very good resolution, position resolution, which allows us to fiducialize the event and to reconstruct the total energy of the track. The plus of optical sensors is a good granularity, a very low noise, and high sensitivity. On top of this, the optical couplings allows to have the sensors outside the sensitive volume, and therefore acquire large surfaces with also small sensors. So this is the Cigno timeline. The project started in 2015 with an intense R&D phase where we developed our initial idea. We started with a 0.1 liter TPC and up to the 50 liter present prototype, which is called Lime. Actually, now we are in the phase 0, where we are finishing to assess the performance of this detector over ground, and we plan to take it underground Gran Sasso laboratories by this fall. This would lead to our phase 1, where we intend to build a 1 cubic meter detector consisting of several modules identical to Lime, and this will be operated and commissioned at LNGS. Our final goal is to propose a much larger apparatus of 30 to 100 cubic meters. So Lemon is one of our prototypes. It has a 24 by 24 centimeter square readout area for a 20 centimeter drift. It is equipped with a scientific CMOS camera, 1 PMT. Here in the drawing, you see the sensitive volume, which is enclosed between the cathode and the gem. The PMT is on the cathode side, and on the opposite side, we have an adjustable length bellow with a lens, which allows to collect the light onto the camera sensors. Here you see a picture of the elliptical field cage and the exploded view of the gem. This is a real picture of 5 seconds of natural radioactivity taken with this device. We use, as I said, a scientific CMOS camera, the Orca Flash 4 by Hamamatsu, which is a very low noise level, a good quantum efficiency, around 70% at 600 nanometers, which nicely matches the emission of the helium CF4 spectrum. So to assess the performance of this detector, we exposed it to an iron 55 source to measure the energy resolution and threshold. Here in these pictures, you see 2 luminous spots, which are compatible with the X-ray emitted by the iron 55. These events are reconstructed with a clustering procedure based on dB scan, and the light collected in the cluster is shown here in this histogram. You clearly see a peak at around 3,000 photons, which allows us to set the energy calibration of around 500 photons per collected keV. On the left here you see the noise level, which is quite low and allows us to work with a threshold of around 400 eV. The same situation is obtained with the PMT, and together the camera and the PMT allows us to reach an energy resolution of 5.9 keV of about 15%. The detector has also been quite efficient, so basically 100% efficiency over the whole volume. So we also assess the tracking capability of this device. Here you see two pictures of electrons, of high energy electrons, 450 MeV. The first one, the electron travels parallel to the gem station, very close to it, about 1 centimeter from the gem. And the other one, the one below, is 24 centimeters away from the gem. You can clearly see the effect of the diffusion, right? And so we are exploiting the diffusion to estimate the Z position of the event. And in these two fields, you see the behavior of the, let's say, the ratio between the amplitude and the width of the signal as a function of the Z, and this allows us to calibrate the reconstructed Z position, obtaining about 15% on Z, while on XY we get something in the order of a few hundred microns. So what about nuclear recoils? For this, we studied the nuclear recoils using an americium beryllium source, and the challenge here is to properly reconstruct the track left by the recoil. To do this, we use the modified version of the DB-scan, an iterative version to connect different clusters, and on top of that, we also used a morphological geodesic active contour to have the full track, as you can see here after a few iterations. So once we have the track, we can determine the track properties such as length, width, light, and light density. These variables are used to disentangle nuclear recoils from electron recoils. For instance, the light density, which is shown in this plot, allows us to nicely separate the nuclear recoils from the electron recoils. So the electron recoils of ion 55 are those showed in gray here. In this way, so cutting on this variable, we can separate the two samples and quantify the signal efficiency of both for nuclear recoils in red, and then the background rejection at the same as a function of the energy. For instance, here at around 6 keV, we have something of the order of 40% nuclear recoil efficiency with 96% rejection against iron 55. We are working on a more refined algorithm that will exploit all the available information. In this picture, you see how a 6 keV nuclear recoil looks like in one of our pictures. So Lime prototype is the one we are currently working with. Is the largest 33 by 33 square centimeter of readout area for 50 centimeter drift, which is about 0.05 cubic meter volume. So on the right side here, you see the pictures of during the construction phase. Actually now Lime is tested overground at LNF and is proving quite stable against hotspot and discharges, and it has also a very good position and energy resolution. This is all thanks also to a new camera, which has a reduced noise, more pixel, and a slightly larger quantum efficiency. The energy resolution, again, for a larger volume is about 15% at 6 keV. And we are planning to take this detector at LNGS by this fall, and this will be also equipped with a water plus copper shielding. So just to give you a feeling of what these pictures look like, so this is a 2D projection over the 50 centimeter drift length of a few milliseconds of natural radioactivity. So this is how it looks like. So our final goal would be to construct a 1 cubic meter demonstrator. So this would consist of 2 field cages placed on the opposite side of a common cathode, which will be closed by two matrices of 3 by 3 readouts of triple gems. So each module is identical to LIME, the prototype I just described, and this detector has been funded and will be installed at LNGS by 2022. So we are currently studying our backgrounds. As I mentioned, we are working with a water plus copper shielding, and here in these plots you see the background, the environmental background in the whole sea of LNGS, and what our shielding would produce. So basically we expect something in the order of 1,000 electron recoils per year, and about less than 10 nuclear recoils per year. So concerning the internal backgrounds, the largest background source is coming from the camera and the lens. Here you see the spectrum of the different pieces of the prototype, and well, we are currently working on R&Ds to reduce the background source of the camera and of the lens, and to bring it below 50 millibecquerel kilograms. Also, the gems contribute a bit to the internal background, and there are R&Ds ongoing at CERN to reduce it. So for what concerns our projection sensitivity, we are working using a 1 keV threshold. Here you see the relative probability to detect a nuclear recoil at 1 keV, and you see the contribution of the different elements in our gas mixtures. So basically helium, carbon, and fluorine. We have evaluated the quenching factor using the SRIM simulation. Here you have the result of such a simulation. You can see that for helium, the quenching factor is relatively large at low energy. We are also assuming to be able to discriminate the head-tail direction of the track, and to have about 30 degrees of resolution. In this way, our signal would look like as the one depicted here, and we are using various scenarios for the background level, which anyhow would be an isotropic background, so the directionality would help us killing it. Here you see the
5 minutes, Andrea.
Yeah, thanks. Here you see the projected sensitivity. So for the spin-independent cross-section, you see different hypotheses. Clearly, we are not competitive with the status of the art of the direct detection, but we can reach an interesting region that would allow us to then move to a bigger device. Also, thanks to fluorine, we are sensitive to the spin-dependent cross-section, and here you see our projections. We are clearly working on new ideas to improve the already good performance. Basically, one line we are working on is to exploit the electroluminescence. Our signal is an optical signal, so if we can improve the number of photons, we would have a better performance. And we need to improve the light yield without increasing the charge yield, otherwise we can have instabilities, and we obtain a nice light yield increasing by just accelerating the electrons in a field of about 50 kilovolt centimeter after the stage of amplification, and this gives us a factor of 6 more light, which is quite good. We are also working on including hydrogen in our gas mixture, and including hydrogen would increase the sensitivity to light dark matter. We have performed tests adding isobutane, which has 10 hydrogen atoms, and we have obtained quite an interesting results in terms of light yield. Finally, to improve the spatial resolution, we are working with negative ions. This has been financed by an ERC project, and the idea here is that negative ions would have less diffusion and thus better position resolution. We obtained already encouraging results at atmospheric pressure. So finally, my summary, I've shown you our project. So the CSIC collaboration is developing an helium CF4 TPC with optical readout. We already achieved with the first prototypes good energy position and direction resolution. We have good discrimination between electron and nuclear recoils, and there are several R&Ds ongoing to optimize the already good performances. Finally, we are planning to go underground at the end of this year with our first prototype, which is LIME, and this would open the road to a much bigger demonstrator, 1 cubic meter by 2022-2023. Thank you. That's it.
Thank you, Andrea. Really cool. So we have time for one, maybe two questions. If there is any, you raise your hand. Yeah, there is one there. Christopher, please go ahead.
Hi there, thanks for the talk. This is a speculative question maybe. I was just wondering, so you showed sensitivity protections for the spin dependent interaction with protons. Is there a technical limitation to running with helium-3 or some small fraction of helium-3 in your detector, which would then give you sensitivity to the spin-dependent neutron interaction? I know helium-3 is expensive, but just from a technical point of view, do you still get the light and everything to get the signals, or does it change anything?
Well, I think this is quite an interesting question. I'm afraid I can't really. Yeah, I don't. I wouldn't. I wouldn't see problems, but I don't. I think we need to investigate a bit before answering this question.
Thanks.
Thank you. Is there any other question? If so, please raise your hand. Okay, I don't see any. So let's thank all the speakers of the session. We're going to take a short break. We're going to connect again 20 minutes after the hour. Depends on where you are. It's 5 p.m. here, but maybe the morning for you. Meanwhile, if you want to stay in touch with some of the participants, I invite you to join the Wonder Me room that is dedicated to the meeting. Especially if you know some good jokes about dark matter, that would be great to share. All right, see you all in 70 minutes.
Hello.
Hi, Rebecca.
Hi. Should I share my slides?
Sure. And exactly, we will start in a minute or so. There's one more person in the Wonder Me that was really disappointing.
Sorry, what was that?
In the Wonder Me, there is only 2 people right now, so nobody's hanging over.
Ah.
I'll just tell the one person there. Start here. In 1 minute. All right, welcome back, everybody. It's 20 minutes after the time, and we're going to start in the session of indirect detection or indirect searches with Rebecca. Lane. Lynn, how do you pronounce your name?
Lynn.
Thank you very much, and I'll give you a warning 10 minutes before and then 5 minutes before.
Great. Okay, so thanks very much for the invitation to speak today. It's a pleasure to be here with you all virtually. So today I'm going to tell you about indirect searches for dark matter. And I want to start with saying why indirect detection is exciting. So the universe has been running experiments for us over very long timescales. So since the beginning of time, we've had systems that are being smashed together, we've had systems that are merging, and we've had things that are exploding. So we have a lot of very extreme sort of situations that we get when we're looking at for dark matter throughout the universe. And really this means that we can uniquely access specific scales. So because we have really big systems, we can look for long particle decay lengths. We can look for much smaller couplings of dark matter particles to the standard model. And we can look for things that are at much higher energies than we could ever have on Earth. And we get all this for free. And I think one of the best reasons to think about indirect detection for dark matter is really that it's dark matter in its natural habitat. So all the evidence we have to date for dark matter's existence comes from its gravitational interactions throughout astrophysics and cosmology. It's the main place we know that it exists. It seems like a great place to go looking for it. So I should also probably define what indirect dark matter searches really are. So I think there are a few different ways you can think about this, but I think the broad sort of definition really is just any search that's looking for dark matter annihilation or decay products from dark matter. So the general sort of picture is you have, for example, if we have annihilation, dark matter particles can annihilate. They can then produce standard model particles, which can then decay, shower, or have some Bremsstrahlung of other standard model particles. And we want to look for some excess flux of standard model particles appearing generally in astrophysical systems. So traditionally, when we think about indirect detection, this usually means we're searching for a standard model flux in dark matter halos, or we're looking for effects of this standard model flux that's produced, how it actually changes these systems. Alternatively, the new sorts of probes that are really gaining traction in the last few years are instead using things like astrophysical bodies, so stars and planets, for example, to look for these sort of processes. So we're looking still for standard model fluxes, but coming from celestial objects, or also looking for the effects of this annihilation, for example, on different celestial objects. So what I'm going to tell you about today is both of these types of indirect probes for dark matter, but I'm really going to focus mostly on the more traditional definition of indirect detection. So I'll tell you about the ingredients for the searches, so what's important when you want to think about indirect detection. Then I'm going to tell you about what I think is one of the most promising potential hints of dark matter that we have at the moment, so the galactic center excess in gamma rays. I'll tell you then really briefly about some other anomalies that we have. I won't spend as much time on any of them compared to the galactic center excess. But then I'll tell you also how we combine all the constraints that we currently do have and what the general picture is for indirect detection and what we might be able to say about particle dark matter moving forward. So I'll tell you then very briefly at the end about these new probes of dark matter annihilation. This won't be in anywhere as much detail as the first part of the talk. But I'll just try and give some motivation about why these types of searches have particularly recently become, I think, interesting and more popular in the community to think about. And how these sort of probes of dark matter work. Okay, so ingredients for indirect searches. What do we need to do searches for indirect detection, and what is important? So the first ingredient you need if you want to do an indirect detection search is some dark matter interaction rate. So this is really just, so for example, if we have annihilation, what is the particle physics prediction for two dark matter particles to smash together and give us these standard model particles, for example? So this really does depend on your particle physics model. Different models will give you different predictions for what this rate will be, but usually it's fixed by the relic abundance of dark matter that we have in the universe today. So if you have a dark matter model, you want to explain how you get all the dark matter to be as much as it is today. So usually what's really driven a lot of our indirect detection searches is this sort of thermal WIMP picture. So the standard idea is that we have dark matter particles in thermal equilibrium in the early universe. The dark matter particles can annihilate to the standard model, and this process goes back and forth in both directions. And then as the universe cools, it starts to only be kinematically possible to have dark matter particles going into the visible particles, though this does depend on what sort of mass you're looking at. The universe expands, and it reaches a point where it's expanding too quickly. The dark matter particles can't find each other in large amounts anymore, and we'd have no more sort of bulk dark matter annihilation. So what happens is we have this thing that's called freeze out, and this gives us the relic abundance of dark matter in the universe today. And this really standard thermal WIMP, so WIMP being weakly interacting massive particle sort of picture. And why I think this is still really interesting to look for is just because it's very predictive. So it predicts a particular annihilation rate for dark matter, which can guide the experiments that we have today. Because if you annihilate at a rate that's too large, then you end up with too little dark matter in the universe today. If it's not annihilating enough, away too much, we get too much dark matter. So it's very predictive in that we have a particular annihilation rate to look for, which is really that we expect of the weak scale. So 10 to the minus 26 centimeters cubed per second. And it also predicts a particular mass range. So generally we're looking at around GeV scale, plus minus a few hundred, a factor of a few hundred, but around GeV scale particle dark matter. And this is where a lot of indirect detection searches really have been focused traditionally in the past. So the second ingredient that we have is the energy spectrum. So this is just thinking again in terms of annihilation. If we have the particles smashing together, what do the energies of the particles look like? So this will also be driven by the particle physics model that you have. The shape depends on primarily the branching ratios you have to different standard model final states. So your model will give that as a prediction. It also depends if you have boosts of particles, for example. So if you have like a dark sector, like cascade decay, giving you lots of dark sector particles, you get a softer spectrum. But this is all determined with the model that you put in. So you can potentially get something that looks more like a continuum. So something like this, where it's just a spread of whatever final state you want to look at. And the important thing to keep in mind is that, for example, if you go to a particular standard model final state, you can still get lots of other particles that you can look at the spectrum of. So what I mean by this, for example, if your dark matter model mostly goes into hadrons, you still get a lot of gamma rays despite the fact you didn't go directly into gamma rays. And this just comes from decaying bromstrahl and all these sorts of things. So we need to put some energy spectrum in. The third thing is the dark matter density and the distribution of the dark matter, particularly if we're looking in the halo, for example. And for this, we really don't know the dark matter density profiles so well. This is a point of ongoing debate in the literature, particularly for our own galaxy. What does the dark matter distribution look like towards the center? We don't really know. And even in other galaxies, there's some good level of uncertainty. So what we really do when we're thinking about the flux of particles that come to us from dark matter annihilation or decay is the line of sight sort of integral over the dark matter density that we're looking at. This will tell us how many particles we end up getting. So for annihilation, this is called a J factor. It's called a D factor if you have decay. Okay, so we want to put all these ingredients together to get some flux. So for just giving you an example, neutral particles, the flux that we end up with has some particle physics component and some astrophysical component, which are those that I just discussed. So for example, we have some annihilation cross-section, something predicted by our particle physics model that tells us kind of like the intensity of the signal. We then have to put in the spectral information that has to do with the model you put in as well. So it'll tell you the spread of gamma rays or neutrinos or positrons, whatever you want to look at. And then we have this J factor or D factor if we're looking at decay. So when we do these searches, we really want to then optimize any of these inputs. So one thing you can do is try and, first of all, have a really large annihilation rate. That can be hard to change simply from the fact that if that's fixed by Rayleigh abundance, you don't have so much room to change that. You can play model building games to try and make it larger in the universe today, if you'd like. For the energy spectrum, we usually want to look in places where the spectrum peaks compared to background. So we're generally, in that case, just looking for a lower background. Or we can really just look in places where there's a lot of dark matter. A lot of dark matter gives us a large signal. So there are lots of these searches that we do at the moment. So what I want to tell you about first, and perhaps in the most detail, is one in gamma rays where we actually do potentially see a dark matter annihilation signal, but it might not be dark matter, we really don't know, but it has a few really exciting features. So this is called the Galactic Center Gamma Ray Excess. So it's highly statistically significant. It's really bright, gives us a lot of gamma rays peaked in a few GeV. So this was first first found in 2009 by two theorists, Dan Hooper and Lisa Goodenough. And it's detected by something called the Fermi Gamma Ray Space Telescope. So Fermi is an excellent telescope. It's been running now for something like 12 years. And this is where we first see the excess appear. So this is just a residual map where we see something bright coming from the center of our galaxy. And the reason why this has been, has really gotten so much attention in the literature is it does present with a lot of the features you would potentially expect of really a really basic class of particle physics models. Being that the signal looks like it has the intensity you might expect of just thermal particle dark matter. So the standard freeze-out picture really matches the sort of annihilation rate you would expect. It's really predicted in that sense to get this particular intensity. The morphology of the signal also potentially can be consistent. There's a number of papers, and I'll discuss this a little bit more later on, that are really debating what this morphology would be. But there are some that find potentially it's approximately spherical, like we might expect from dark matter, and it really extends well out of the plane in the center of our galaxy. The spectrum of this signal also is consistent with something we might expect from dark matter, in the sense that it's invariant with the position in the galaxy and its shape. It's not getting softer as we're going further away, that it's using energy, kind of implying the thing that's producing this signal is locally producing it. So if it really is a dark matter signal, it's something we want to get to the bottom of, simply because we don't have any evidence so far for any dark sector, visible sector interactions. So really, when we think about if this is a dark matter signal, if it's something else, the key or the leading something else, something called pulsars. So pulsars are just rapidly spinning neutron stars. And the main reason why I think the most convincing piece of evidence we have potentially for this signal coming from pulsars is just that they can also match the gamma ray energy spectrum, in particular millisecond pulsars. So pulsars appear as something called point sources to Fermi, which just means that they have angular extent below the detector thresholds. So I'll say point sources and pulsars probably interchangeably. Pulsars is just the physical interpretation you can keep in mind. potential explanation, I should say. So if we think about point sources as the excess, you might also wonder if it's just pulsars, why can't we just look at them, detect them, measure their spectrum, and then call it a day? The reason this doesn't work is this category would be resolved point sources. So that's those that are bright enough to be individually detected. And we've tried to do this so far, and it doesn't look like anything that we've found really convincingly explains the excess yet. So the category that potentially can explain the excess are called unresolved point sources. So these are point sources that are too dim to be individually detected. But you could imagine collectively, if you have just a lot of them, that the flux across a lot of these very faint sources could add up to give you the galactic center excess. So this is the class of point sources we want to think about, ones that are really, really faint. Maybe just one really, really faint. Okay, so how can we tell the difference between these two different hypotheses? Thankfully, we can look at the counts of gamma rays. So this has been something that's been investigated in some detail, being that the counts of gamma rays you get from point sources really exhibit different statistical behavior compared to those coming from annihilating dark matter. So if dark matter is coming from, if the signal is just coming from dark matter, we expect a smooth continuous halo, at least approximately smooth. So just from simulations, we expect something that looks kind of like this. If we have point sources instead, we expect just more of a clumpy signal. So you can imagine in a given pixel of the sky, you might have no sources. You can imagine in another pixel, you might have a lot of them. So the pixel to pixel variance can be quite high. So we really want to then just think about what statistical methods can we use to try and exploit the fact these statistics look different. And one method that's been really popular for a number of years is called template fitting. So for template fitting, we build up a picture of the full sky by breaking it into components that come from some model, some ansatz, or just really things you think that might be there. So as an example combination, you could have just the isotropic background. You can have then diffuse emission. So this is something called the Galactic diffuse emission model. This one comes from cosmic rays interacting with the gas and the starlight, and it makes up most of the gamma rays that we look at in the center of the galaxy, something like 80–90% of the gamma rays, depending on really what region you're looking at. But this makes up most of the gamma rays we have. We don't understand it very well, which I'll say in a few slides, I'll explain in a few slides, really causes a lot of problems. Then we can put in structures like the Fermi bubbles. So this is just a big structure above and below the plane of our galaxy, which we think emits in gamma rays, as well as something for the excess. So you can really build up a picture of the gamma ray sky by modeling these individual components. And you just let all the components float in a fit to see if more of a smooth or clumpy picture is best preferred for this excess template. So this is the shape of the excess potentially in this case, and we want to look if it's smooth or clumpy. The other method that's been really popular is called just the Wavelet Technique. And in this case, you're using a wavelet transform. So you can think of it kind of like a Fourier transform, just to look for peaks in the data. So it's the same sort of principle. Something that's clumpy, so looking for peaks, would correspond potentially to point sources. Something that's smooth, so if we don't find peaks, this either means there aren't point sources there, or they're just so faint that they look smooth. So it's the same sort of thing, clumpy or smooth, what's the answer? And as of 2015, it looked like the answer was clumpy. So both these two independent methods found clumpy picture looks best for the excess, two independent groups. And I think really at this stage, this kind of became, I think pretty broadly in the community, the accepted answer. It looks like it's point sources. We found this two different ways. I guess that's the end of things. And it kind of stayed like that for a couple of years. But both of these results actually needed some level of interpretation as of 2019. So together with my collaborator, Tracy Slatcher, we showed in one paper in terms of this non-Poissonian template fitting that really if just you get the templates wrong, you can miss a dark matter signal, was the simple point. So what we did was we just injected dark matter signals into the real data and we found it didn't find it. So this is just doing some Bayesian analysis, how much flux do you actually reconstruct? And if there's no dark matter, you find just point sources are picked up and no dark matter's there, but we start injecting it and you see there is no dark matter that's recovered in these cases. So there seem to be some systematic effects that we really needed to think about. And really interestingly, actually in the same year, we needed to think about how to interpret these wavelet results as well. So in the time since this 2015 result had come out, Fermi had released a new point source catalog. So a point source catalog is really just a list of point sources that we think we know are there. So they're sufficiently bright for Fermi to actually finally see them. And usually it gives you some information about what we think the sources are. So it turns out if you actually overlay this wavelet technique where it actually finds the point sources, what's circled in red are members of this new catalog. So what's really interesting is it's like this method works so well. It found point sources before we even knew about them. So it was definitely right. But once you actually have this updated information, then you can ask, does this actually explain the excess? Because you can go into the list, look at the properties of the point sources that are there and see if they're compatible. And the really short point of this is that no, the bulk of these point sources can't explain the excess, in the sense that you can look at some of them. Some of them are things like extragalactic, which means they're not actually in the galactic center at all. So this means the sources that had been found previously really don't explain the bulk of the excess. And we have a new problem, which is, well, if all the peaks we previously found, or the bulk of the peaks we previously found, don't explain the excess, then where is it? If it's point sources, maybe it should have shown up. That is a question. The other thing is, well, maybe the point sources are so faint that they don't show up, but then you need to have more of them to give you the right sort of flux. So there have been a number of papers since then looking at what sort of things we can do better. So one example is looking at terms of this injection test, just finding dark matter in the data can be improved if we just get better foreground models. So these galactic diffuse emission models are, as I was saying, not very good. If we improve them, this issue to some degree is improved and it won't necessarily be there. So that was pointed out in this Bushman et al. Paper last year. But more broadly, there are still really a lot of systematic issues that plague these galactic center excess searches. So for example, in a couple of papers together with Tracy Slatcher that came out last year, we looked at really what happens if you try to some degree to improve your modeling in the sense that if you just give templates more freedom. So if the issue is we don't know how to build up the right picture of these different templates, and we have to, we want to get closer to something that's the right answer, we tried things like just breaking templates into pieces. And we found if we do this, we potentially can just remove point source evidence as well. And in this sense, we can just get, if we do this modeling with these extra pieces, breaking the templates into extra pieces, and then making simulations based on this, this scenario where the templates have more freedom, we find that doing a fit with the old pipeline can give us these spurious point sources. So in the sense that you can really easily, it seems, well, you can to some degree fake the evidence for point sources just by getting your templates wrong as well. So really just the short point is there are a lot of systematics we have to think about before we make any robust claims about what the excess is. The galactic center is a very difficult region to get right. And to give you perhaps a more explicit example of why this is true, what I'm showing you here, so this is a result from the Fermi collaboration a few years ago, how their point source catalogs vary with different background models, or perhaps I should call them foreground models. So just these models that make up most of the gamma rays that we can't model very well. If you look between these two different background models and look at what are the point sources that you find with high significance. So the last few searches I was telling you about are sub-threshold searches because the point sources are fairly faint. If we think about how well can we even determine ones that are really bright, so resolved point sources. If you change the background models, they find totally different point sources at 5 sigma. So the claim is at 5 sigma, we can find different point sources, but they'll appear with one background model and not the other one. So really the answers can just really drastically vary depending how we do a lot of these these sort of models. So the key point in the end really is that all of these models that we have are really not good fits to the data. And while we don't have a model that is a good fit to the data, it's really difficult to make any sort of robust conclusions as to what's going on. So I think the current picture with the galactic center excess is really just, there's lots of debate. I think no one robustly really knows what's going on. But there are a few things we can do to try and understand it. So just briefly to kind of point out some of the current points of tension that people are wondering about. One key thing really still at the moment is the morphology of the signal. So if it looks more like something we'd expect from a dark matter density profile, roughly spherically symmetric, it would look more something like this. But there have been a number of papers recently that find a preference for a morphology that looks more like the stellar bulge. So really, if it traces the stars in our galaxy, that would be much more consistent with it coming from pulsars or, some new astrophysical phenomena rather than from dark matter. So a number of papers that you can check out here that have been looking at this. I think still we don't robustly know if this is the answer though, simply from the fact that the models that we're using are still not very good fits to the data. So if you're comparing two different hypotheses, if I take one set of models and put in, for example, this bulge sort of morphology as the excess template, or I then take one that looks more like a dark matter density profile, but all the other models that we use with it are not very good fits. We're still comparing two different models or two different fits that neither are formally good fits to the data. So there's no way to know that if we just improve these background models or improve these other things we can't model very well, if the answer then also changes as soon as we do that. But this is for sure, I think, an interesting ongoing investigation in the community at the moment. In terms of the energy spectrum, it's still comparable to millisecond pulsars. It can be fit well also with dark matter. I think on that end, either side is just fine. In terms of the intensity, I think the signal really is better explained, I guess, by dark matter in the sense that if you really do believe thermal dark matter, this is the intensity you would expect of the signal. On the other hand, for pulsars, the fact that when we do these searches for the peaks and don't actually see anything there, implies then probably if it really is millisecond pulsars giving us this signal, they should be really faint. And if it's really faint, we need a lot of them. And then you can start asking, well, how many pulsars can I actually reasonably expect to have in the center of the galaxy? And I think at the moment, there's really quite large numbers and not at all what we expected. So we're really looking now at something like at least tens of thousands of these. So there's some question is, how do you get this many? What would you expect? There was an interesting paper recently actually looking at how potentially you might have something like tens of thousands of pulsars in the center of the galaxy. But this is something to also keep an eye on. Okay, so other avenues to actually kind of settle this debate. How can we find out what's really happening with this excess? Well, one thing we can do is try and detect the pulsars, if they do exist, directly in radio. So they might pulse into radio. We can use upcoming radio telescopes such as Meerkat to actually try and find them directly. Another thing that's become, I think, fairly important more recently is thinking about alternate ways to do these fits. So there are a lot of systematic issues with the techniques that we use. So if you can really think about what are the alternative ways to try and statistically explain what you're seeing, you can have complementary systematics to try and hopefully move towards something that gives you something that is just more accurate. So there's a number of these that have been looked at recently. You can check out those papers there. The status overall, though, is just that I think nothing totally agrees and we're not completely sure really what's happening. Another thing that we can do is look at the energy spectrum actually in lower energy gamma rays. So the systematics really are quite large for Fermi below a GeV. And this is where the energy spectrum, I think, deviates the most with the expectations you might have from dark matter versus pulsars. So new MeV gamma ray telescopes can shed light here, just with the systematics that are much lower. Okay, the other thing is if it's really dark matter, you would expect to see it somewhere else. And you would want to look at the constraints that we do have from indirect detection just on dark matter annihilating to gamma rays in any other place. So I think that perhaps the most robust constraints that we can think about are those that come from dwarf spheroidals, or perhaps just the best. The reason they're the best probably is just that they're very dark matter dense. They don't have a very large standard model background. So they should give us a good signal. I think the status for dwarf spheroidals at the moment is not, in terms of the tension we have with the galactic center excess, is not strong. Though I think if the galactic center excess really is dark matter, a signal really likely should be appearing here soon. So this is the result from the Fermi collaboration a few years ago. So this dashed line is just the thermal raylet cross-section. So the annihilation cross-section is the y-axis. We have dark matter mass on the x. So here are a few different fits to the galactic center excess. You see, well, okay, looks like maybe there is some slight tension. Keep in mind, this is also 100% into BB bar final states. But one thing we also really have to keep in mind, even with these dwarf spheroidal searches for dark matter annihilation, is there are systematic issues here as well. So it was pointed out in this really nice paper last year, if you just put more informative priors in when you're actually doing these fits, you can see you get an answer that can be different by a factor 2 to 7. So potentially, while you have, from the Fermi collaboration, you might expect something down here, the limits can actually be much lighter. If they're much lighter, then the GC potentially is totally fine. But that's not all. So there was a really interesting paper also last year by Laura Chang and Lena Nasib looking at really, do we have enough kinematic stellar data to be making the sort of claims that we are? Being that when we want to infer how much dark matter really is in these dwarf spheroidal galaxies, so these are just the way satellite galaxies of the Milky Way, when we're looking at how much dark matter we think might be there, we need the stellar data. This is what informs, the kinematic data of what's really happening. And a lot of, actually a lot of the dwarfs that we use don't have a lot of stars that we understand very well. So there are really a number of systematic effects we should be thinking about when, when we see these results, how much we really trust that this is robust and there isn't, potentially not something wrong, but potentially they shouldn't be as strong as we think they are. Okay. All right, so that's what I wanted to say about the galactic center excess. I'm going to tell you just really briefly about another excess or two, very, very briefly in comparison. So another one is the anti-proton excess. So this is an excess in antiprotons detected by AMS. It can be interesting from the dark matter perspective, simply that it's also potentially well fit with just thermal WIMP dark matter. And typically we're looking at something around 50 to 150 GeV as the dark matter mass for this scenario. So when this excess was first found, the significance was claimed to be around 4 sigma. There's a lot of debate with this excess really at the moment in terms of, again, systematics. How robust is this, and really what is the significance of the signal? And there are a few reasons that this actually becomes more complicated than we'd like, particularly that, so AMS, the telescope that detects this, doesn't release its correlation matrices. So these uncertainties are correlated bin to bin, but we don't actually have these matrices to use. So we need to really try and quantify systematics without all the information we might like. So there have been a number of papers trying to quantify the systematics, but the answer really can vary between, over 5 sigma to 1 sigma. So you can check these out for more details if you're interested. But the status at the moment is, I think people will tell you, this is different levels of significance. So I don't think this one is as robust as the galactic center excess, in the sense that I think the galactic center excess is something. This one, I think we don't know yet if it's, just a systematic effect, if it's really there. It is interesting from the point of view, though, that potentially if it is a real signal, it can overlap with the galactic center excess. So, with everything we do in indirect detection, because astrophysics always has this problem of how well do you understand your systematics, you always want to see a signal somewhere else. So if the galactic center excess really is dark matter, I think, you'd want to start seeing excesses in other channels as well. So it was shown in this paper that, you know, if you have around 50 GeV, which is a good explanation for both, you can explain both these excesses. But I think the systematic, the significance of this signal is not really totally robust at the moment. Okay, I was going to tell you about the positron excess, but I think I'm going a little bit slow for time. So I might just go straight to the constraints that we have at the moment from indirect detection. So there are really quite a number of telescopes that are looking for dark matter and can give you some bounds. I'm choosing to show you those that are the strongest for each channel, because I think this is relevant if we want to build up a picture of how well have we thought about excluding, you know, just thermorelic dark matter. So the strongest and most robust bounds that we get for low mass dark matter comes from the cosmic microwave background. So this comes from dark matter just annihilating into ionizing particles that can then mess up the CMB. So on all these plots, the y-axis is the dark matter annihilation cross-section. The x-axis is the dark matter mass. And so generally below about 10 GeV, we can get, depending on your final state, you can get fairly strong constraints. So this dashed line is that gives you the relic abundance with just a 2 to 2 WIMP. So we can have fairly strong constraints from the CMB. This comes from the Planck satellites measurements. The strongest for hadrons, so if you have a model that goes into a lot of standard model hadrons, generally you want to use gamma rays. So the best limits in that case, we use the Fermi Gamma Ray Space Telescope looking at these dwarf spheroidal galaxies, as I mentioned to you a couple of slides ago. They can have systematic issues as well, but the general sort of picture is it seems like, you know, we can probably constrain something up to, you know, a few tens of GeV depending on what final state you have. If you want to set limits on any model that gives you a lot of leptons, generally the best thing you want to look for is, so these are positrons, so the AMS positron search. And in this case, you also can have fairly strong constraints for these lepton final states being up to order as well, a few tens of GeV. And in this plot, actually, already we have taken quite a conservative scenario. The general thing with charged cosmic rays is thinking about, you know, magnetic fields, propagation, and you can get a number of uncertainties there as well. But I think the general picture is probably it's okay to say above a few tens of GeV for leptonic final states, we can get some pretty good constraints. Okay, so the general picture when we put all of this together is you can think about, okay, we have all these different experiments, they're complementary, they can probe different final states more optimally. And when dark matter annihilates, it can only really go to some selection of final states. Branching fraction has to add up to 1. So it only has so many states it can go into. And if we think about a model that goes a lot into gamma rays, then maybe we don't see it so much in the leptons, but then we can constrain it using Fermi, for example. So what this plot is showing really is just the combination of all the different visible final states that you might be able to constrain. So you could just think about it as combining the best limits we have for low light dark matter coming from Planck satellite CMB, combining the gamma ray data we can get from dwarf spheroidal galaxies with Fermi, and combining the positron data we can have with AMS. And we find if you just put all of this information together by looking at these visible final states, so this is just standard 2 to 2 annihilation for an S-wave thermal dark matter candidate, we only actually at best can exclude about 20 GeV in the dark matter mass. And what this really means is if we think about the standard thermorelic cross-section that's really available, most of the parameter space is really still open. There is some level of discussion in the community that maybe, you know, the WIMP is really dead. I mean, this is also driven a lot by direct detection and collider constraints. But really the only thing that you can compare to as really a solid benchmark is what is the relic abundance? That's the property really tied to this thermal dark matter. And this prediction is you can only directly probe by looking at the annihilation rate. If you want to make any other sorts of constraints, you need to use some particular model to link direct detection and collider physics. In this case, you really just have one thing, the annihilation rate that sets this, and we need to use indirect detection really to probe it. And at the moment, really, there's a lot of exciting progress that we can make, but we haven't really made it just yet. We still have a number of orders of magnitude that we haven't robustly thought about trying to exclude, this standard sort of width. Okay. So I think I have about 10 minutes left. So I'm going to now just try and really briefly tell you a little bit about these new probes of dark matter annihilation rates. So this is moving away from the traditional indirect detection to some new things that we can think about now. And I'll only really speak about this section very briefly. But the general picture is, so before I was telling you about dark matter annihilating just in the galactic halo, but you can think about dark matter annihilating inside objects that capture the dark matter from the halo. So the general picture is that you have dark matter whizzing around in your halo. It can scatter off some celestial object, being a star or a planet. It can scatter, lose energy, become gravitationally captured. And if it's the type of dark matter that does annihilate, this ball of captured dark matter particles can annihilate, give you standard model products, and these potentially can just be absorbed by the object. And so absorbed in the sense that the annihilation energy is just absorbed by the star or the planet, which can increase its temperature. It can also give a number of other observable effects. Temperature has been very popular recently. And just to really motivate why we do these searches, well, I'll tell you a bit more about that in the next slide. But in terms of the optimal sort of object we want to think about, you might wonder when you see more recently people thinking about all sorts of objects we can use to look for dark matter, why we choose them. Is it completely arbitrary when we just think about looking in some other different target, different astrophysical object? Well, there are a few things that we really want to look for when we do these type of searches. So one thing is the radius of the object, or at least the effective capture radius. So if the object is just bigger, more dark matter passes through it, and it can end up capturing more dark matter because of this, and this can then give us a larger annihilation signal, just speaking in really approximate terms. So generally a large object is pretty good if you want a large flux. It's also really good to think about objects that have a very high density. And if you have a high density, then really the key thing is that you can be sensitive to much lower cross sections, so much lower scattering cross sections. So scattering when the dark matter scatters with the object and then becomes captured. So dense objects are great if you want to look at really sort of small scattering cross sections. The other thing to really think about is the core temperature of the object, in the sense that if you have a very hot core, that can give kinetic energy to the dark matter particles that have accumulated in the core, and it can give them just a thermal kick, and they can just evaporate and leave the system, and then you won't be able to probe them. So really you want to optimize over these different sort of properties to find what the best object is. What the best object is will depend what telescope you're using and where you're looking. But these are the reasons why we really want to look at lots of different objects, because different searches are optimized in different ways. And really the key reason I think these have become quite popular recently in the last few years is simply because we have new technologies that are really amazing. And we're going to learn a lot about, I think, dark matter, or more broadly, I guess, really just about the universe from the fact that we have these new technologies. So for context, the coldest sort of objects that we have are around 50 Kelvin. So this is pretty deep in the infrared. So the target window to look at for things like dark matter heating usually is then just the infrared, because of course, if it's going to heat it, it's going to at least heat it above your background expectation. So we can't go in that direction. We want to go to higher things. And a big part of the motivation then comes from these new telescopes we have that are going to be capable of looking at objects in the infrared or any higher sorts of, shorter sorts of wavelengths. So Hubble has been doing this already for a very long time. It's been excellent. It can give us some information about some objects already. But one that I think is really the absolute powerhouse is GWST. So this is going to be really exciting when it launches. We're going to learn so much, and hopefully it really does actually launch. For those of you that have been paying attention, it's supposed to launch now 18th of December this year. So potentially in a few months, we're going to really see this launch finally after a very long time of waiting for this to happen. So that is going to be great. But it's not just JWST. We have a number of really interesting telescopes as well. So particularly Rubin, which should be getting first light in the next couple of years, can tell us some things about these searches as well. And also can Roman. So the Roman telescope hopefully will launch within the next 5 years or so. I think this might have recently been just pushed back to 26. But this telescope also will be capable of seeing things in the near infrared and also the shorter wavelengths up to optical. So really having this new suite of telescopes and detection technologies, I think has really driven the relevance of looking for dark matter in these astrophysical systems. Before we might have thought, you know, this is something we can do. People have thought about dark matter in celestial objects for something like 30 years by now. But no one had been thinking in the level of detail we are now, just because we have so much data that is hopefully coming up very soon. That's going to tell us a lot about how these work. So I think I have
5 minutes, yes.
5 minutes, yep, okay. So I'll wrap up in a second. In terms of what sort of objects really we want to use with these searches, I'm not going to tell you in any level of detail about the searches. There are a few really interesting talks coming up soon after mine about looking for dark matter in these objects. So one of the best systems you can use are neutron stars. And this is simply because they're just so dense. So they're going to give you the best cross-section reach. You can look at a number of the papers here. There are so many papers on this topic. You can see the interesting talks today on dark matter and neutron stars. But really the key point is if we want to get the best reach in the scattering cross-section, neutron stars are the way to go. They're very small, which makes them more difficult to see with your telescopes. But there are good prospects, so hopefully we'll be able to do this. The other one is if you want to look for something a bit bigger, it's great to use exoplanets. And the reason why really they're great to use is you can see them quite far into the center of the galaxy. So potentially exoplanets can give you a probe of the dark matter density profile. So I told you at the beginning, it's not something we know very robustly. But potentially if you have more dark matter in the center of the galaxy, you could get more heating. So this plot on the left here is showing you just as a function of distance to the center of the galaxy, how hot some planets might be. So if we have dark matter heating, we see we might get this uptick if we have more of a sort of spiky sort of dark matter density profile. Compared to those exoplanets where we don't expect to have heating, the temperature is much lower. So we can't do something like this with neutron stars simply because we can't see neutron stars this far away. So exoplanets are going to be great in that regard. And we get some pretty good new probe of the dark matter scattering rate. But there are lots of different other objects you can use also that are really big that give you other sorts of observable effects. So you can also see a really great talk later on today on population 3 stars and dark matter as well. Okay, so in summary, I told you about a few different directions in indirect detection today. So I spoke about this traditional indirect detection, particularly I was telling you about this galactic center excess in terms of the fact it might be dark matter, it might be pulsars. It's really hard to say at the moment because we just can't model things very well in the center of the galaxy is kind of is the punchline. There are other anomalies that do exist, lots of ongoing investigations. I think we don't have anything, we don't currently have anything where we robustly think we have a dark matter signal. Generally, the ongoing theme is systematics, given its astrophysics. But really, if we want to find a dark matter signal in astrophysics, we will want to find something in a different system as well, even if it is astrophysically, that can corroborate if the signal is really there. So for example, for the galactic center excess, something like the anti-proton excess would be great, though that also has problems of, you know, do we really trust how significant this signal is? In terms of the total constraints we have from indirect detection at the moment, I would say the WIMP is really far from being ruled out, but there's a lot of interesting progress we could make going forward with new telescopes. I also spoke really briefly about these new astrophysical searches for dark matter in celestial objects. And really a key reason why these are so exciting now is we're going to have data really soon. And I think this is going to allow us to make a lot of leaps forward terms of understanding how dark matter might affect these systems and in terms of what dark matter actually is. Even better, hopefully we might be able to find dark matter in one of these systems. So that's all I wanted to say. Thanks for your attention.
Thank you, Rebecca. Very, very nice. So we have time for one, maybe two questions. Nirmal.
Hi, thanks, Rebecca. Great talk. So maybe not to be facetious, but to combine the two parts of your talk, could you probably, is there room for the Galactic center excess to be explained by dark matter annihilating inside pulsars?
Inside pulsars?
Yeah.
Yeah, so this is actually possible. So I'm not sure if this is the version you also mean. So a way you can actually do it that combines both of these sections that I spoke about is if you capture dark matter in pulsars and dark matter then annihilates to something that has a sufficiently long lifetime. So if the mediator between the dark sector and the visible sector is really just long-lived or very boosted, it can give you gamma rays that appear on the outside. So I actually wrote a paper together with Tim Linden, Payal Mukhopadhyay, and Natalia Toro, looking at a signal for gamma rays you can have from the galactic center region using a whole population of neutron stars, or pulsars also will work.
Right.
What was really actually funny about that was, yeah, you can get something of the size of the galactic center excess. We didn't look at it actually in any detail. We just mentioned this in about a paragraph as a kind of funny coincidence because we weren't planning on actually trying to do that. The thing with that was really that the sort of intensity probably you want for the galactic center excess in that case is, if you look at the model space, potentially constrained by direct detection to get the right normalization.
I see.
But it might not be a difficult model building challenge to actually get around that. But because it wasn't just sitting there in totally unconstrained parameter space, we didn't go after it, but that's actually something that could be interesting to look at.
Indeed, indeed. So, yeah. Very interesting. Thanks.
Yeah, thanks for the question.
All right, thank you. So I don't see more hands being raised. I have a question, but I'll ask it in the Slack channel, if you don't mind. We need to move on to the next speaker, which is Javier.
Yes, can you hear me?
Yes.
Okay, so I will share my screen now. Let's see. Okay, on presentation mode.
We see it.
Okay, perfect. Can you see the slide changing now?
Yes, it works.
Okay, perfect. So thank you very much for the opportunity to present this work in this forum devoted on searches for dark matter subhalos with the Fermi-LAT telescope. This talk is on behalf of the Fermi-LAT collaboration. So this is the general picture for any dark matter search, astrophysical dark matter search. You have dark matter, you have standard model particles, and you want some process between them in the WIMP paradigm. And basically, depending on how you read this diagram, you have production searches, direct detection, and indirect detection. Of course, more details of this has already been mentioned by Rebecca on her talk. And we're interested on indirect detection, so dark matter particles interacting and giving rise to standard model particles. Now, these particles, they can self-annihilate or decay into these standard model particles. And some byproducts of this process, you can see in this picture, are cosmic rays, neutrinos, and photons, finally. And photons are somehow a golden channel because they are not deflected by magnetic fields. Cosmic rays being charged particles, they would be deflected. And they are much easier to detect than neutrinos, of course, as we all know. And they don't have any relevant energy losses at the scales where we are looking for dark matter, so local universe. And therefore, they are a golden channel. And these photons, given the energy range of the mass range, sorry, of the weakly interacting massive particles, they would be gamma rays in the MEV range in principle. So we have to talk about gamma ray astrophysics if we are going to look for dark matter with them. We have mainly two types of observatories, space and ground base. And as you can see, the space base is satellite, but the ground-based telescope is nothing similar to what we have in mind when we think about a telescope. It's a Cherenkov telescope, and its behavior and it's very different to anything related to optical or ultraviolet telescopes. So I'm not going to talk about that. Just to say that both types are complementary in energy range, for example, sky coverage, etc. The Fermilab telescope, it's been operating since 2008, so more than 10 years now, and it detects photons from more or less 20, 30 MeV up to 1 or 2 TeV, so a very wide range in energy, with energy resolutions of 20% at 1 GeV, a huge field of view with a 2.4 stereo-radians. This means that Fermilab can survey the whole sky in more or less 3 hours. We can obtain a full sky map in 3 hours. And its angular resolution, I will come back to this, but it's more or less 0.1 degree at 10 GeV. As Rebecca mentioned, anything below this value is undistinguishable from a point source for Fermilab. And it has an effective area of 1 square meter, of course. It's a very small device. So this is what Fermilab has been surveying in 8 years. This is the sky in gamma rays in galactic coordinates. So this prominent feature here horizontally is our own galaxy, of course. And you see also a lot of point sources. When you decompose this sky into its components, you have a galactic component, which is due to inverse Compton, Bremsstrahlung, and pi-zero decay processes. You also have thousands of point sources, individual point sources, most of them extragalactic, but some of them also are galactic. An isotropic, very far away background, and maybe we have dark matter hidden here somewhere. So where to look for dark matter in this map? When you go to a simulation, a dark matter only simulation, this is the prediction for the dark matter annihilation signal. And as you can see, the most dominant source here is, of course, the galactic center. And then you see lots of points here. So the question is not only if we can search for dark matter here, but have we already detected dark matter? In other words, is this map hidden in this map somehow? Well, we'll see. These are some of the targets we can take a look to. Of course, again, the talk by Rebecca, she mentioned some of these targets, and most importantly, the galactic center, which is the most relevant target here. We have also the halo of the Milky Way, some galaxies, the dwarf satellites, the extragalactic background, and spectral lines, which cannot be fitted exactly in this map. And finally, we have dark satellites, which is the topic of this talk. So what are dark satellites? Well, to take a look at these dark satellites, we have to go back to the cookbook for dark matter annihilation. This is a slightly different version that Rebecca has shown for the flags of dark matter annihilation. We have here the gamma ray data. So what do we see in the sky? Then we have this J factor, which is an astrophysical factor and tell us how much dark matter and how is it distributed. And finally, we have this N gamma, which is a particle physics factor and tell us how does dark matter annihilate. So when you go to this J factor, this astrophysical factor, to study the structure of the Milky Way, for example, you can rely on some observations, but on the low mass scale, you have to rely on n-body cosmological simulations. And this is an example of a simulation. This is the Aquarius simulation by Springle et al. And this would be the Milky Way halo, okay, everything in this picture. And as you see, the real radius, which is not to scale, anything is to scale here, is just for illustrative purposes. The real radius would be much larger than the actual baryonic galaxy, what we understand as our galaxy, and we will be around here. And of course, the largest of these subhalos, they call it subhalo because there are halos within the dark matter halos. This is the substructure of dark matter. The largest members of this population will host the dwarf galaxies. But we can ask ourselves, what about these smaller ones, but very close to us? So depending on the particle mass, the particle model you are using, these subhalos are expected to have masses as low as 10 to the minus 12, 10 to the minus 6 solar masses. To give a taste, 10 to the minus 6 solar masses is roughly the mass of the Earth. So very, very small subhalos. Any n-body cosmological simulation is incomplete due to numerical resolution. This is because the subhalo mass function is a power law with negative slope. And this means that as you go down and down in mass, you go up and up in number of subhalos, and this at some point will numerically diverge. And we are using the Via Lacta 2 n-body cosmological simulation, which is another competitive one. This resolution, this mass resolution, is 5 million solar masses. So maybe we are losing subhalos below this mass with very relevant J factors. How can we tackle this problem? Well, we can characterize this original simulation, and by using some lambda CDM recipes, semi-analytical recipes of structure formation, we can generate mock realizations of this simulation by pushing down this mass resolution limit. So we are pushing down, by the way, this mass resolution limit to just 10 to the 3, 1,000 solar masses, so more than 3 orders of magnitude, a very large improvement. And this will be the general picture. In the y-axis, we have the J factor, which is a measure of the brightness in gamma rays of a target. The x-axis will be the distance to the Earth in kiloparsec, and the color scale will trace the mass of the subhalo. Therefore, above 10 million solar masses, we have the original simulation, and this is our repopulation. Nothing in lambda CDM tells us that this shouldn't exist. This must exist. It's just a numerical issue of the simulation that we are not seeing this in the original simulation. Okay, so some of these, not all, but some of these will host the visible dwarf satellite galaxies, and everything here below, more or less 10 to the 7, this number is under discussion, but 10 to the 7, 10 to the 8 solar masses would be dark, meaning that they are unable to retain any baryonic content, therefore would be completely invisible. They are dark satellites, okay? And the point here is that when you go to the J factor, some of these dark satellites are among the brightest subhalos. The brightest dwarf galaxies here are competitive with these dark satellites. So they are in principle good targets. Now, as I mentioned, they will be completely invisible. And therefore, if they are annihilating within the wing paradigm and emitting gamma rays, they would appear for Fermi-Lat as unidentified sources, NIDs. And when you go to the same map as before, but sorry, this shouldn't be happening here, but I'm sorry for this. This is a map of Fermi-Lat, but decomposed by the class of the object, the source class. And you see that nearly 1/3 of the sources, or roughly 1,500, are NIDs. So maybe some of these sources are dark matter subhalos just discovered, but awaiting proper classification. So we can also use some filters to reduce the pool of these, as I mentioned, 1,500 are a lot of individual sources. To reduce them, we can apply some filters according to the expected dark matter emission. We can reject them. These are some of them. For example, the flux variability. We don't expect the dark matter annihilation to show any variability with time. So if a source is very variable over this time with Fermi-Lat, it should be immediately rejected as dark matter subhalo. And there are also other filters, as you can see here. This filtering turns out to be very efficient. In the case of this catalog, this very famous Fermi-Lat catalog, 3FGL, we have 1,000 of unidentified sources, and after this filtering, we are just keeping 16. So we are ruling out more than 90% of the catalog. Very, very efficient filtering. We also, when you go to this master formula and invert it to obtain the sigma v, the cross section as a function of the rest of the ingredients, we have this F min here, this flux. And this would be the sensitivity of the LAT to dark matter subhalos. This is actually the required flux to have a detection, a 5 sigma detection over the background. This is naively taken as a threshold flux of the catalog, which is a good approximation in principle for a point source. But in the case of dark matter, we have an important dependence on the wind mass, the annihilation channel, the source sky position, and catalog setup. So this has to be taken into account to perform a systematic search of dark subhalos, dark satellites. Intuitively, of course, a dark matter subhalo placed here will require more flux to be detected, to have a 5 sigma signal over the background, that one here, because this is a more quiet zone, a more easy zone to detect things, okay? And we compute this minimum flux, its sensitivity. And as you see in this catalog, I mentioned the 3FGL. If you assume WIMPs annihilating into BB bar channel, we can center, these are the galactic latitudes, they're important. If you see the blue points, for example, you see that the flux, depending on the mass of the WIMP, varies more than 1 order of magnitude, almost 2 orders of magnitude, depending on you are dealing here with very light WIMPs, very heavy WIMPs. So it's very important to take into account that the LAT is much more sensitive to heavy WIMPs in this catalog. For example, in this other catalog, which has a different configuration, we actually have more or less the same flux regardless of the mass. Light WIMPs and heavy WIMPs are more or less the same. As you see here, the scale is much narrower than before. So anyway, it's important to take this into account. Once we have a short list of candidates, we have 44 candidates, we can perform a dedicated spectral analysis. And we have improved statistics. We have now 10 years of LAT data when we did this paper, and we are able to favor or disfavor the dark matter hypothesis. We use the Fermi Pi software for this analysis. So we are, for each of these candidates, we are performing a point source detection map. We are modeling the region, and we are doing the spectral energy distribution. So the flux versus the energy, basically. And we work with 3 astrophysical parameterizations, a power law, a log parabolic model, which is a power law with some curvature, and a super exponential cutoff power law, which is a very, very curved spectrum, very similar to that of pulsars. So these are the astrophysical parameterizations. This is used for pulsars, but it can also be used for dark matter. As Rebecca mentioned, pulsars and dark matter, are very similar in their spectrum. And we can perform the likelihood of each model with a generalized generalized likelihood ratio test, which includes the difference in the degrees of freedom. In principle, we will require a delta TS larger than 25, which would be in principle equivalent to 5 sigma to have a positive detection of dark matter. We are not saying that. Our best candidates have a delta TS around 10, so not strong enough whatsoever. Nevertheless, as you can see here, the spectral energy distribution follows very nicely the experimental points. This solid line here would be the best fit, in this case, annihilating into BB bar. And these are the experimental points detected by Fermi-LAT. And the fit is very, very good, actually. Of course, there is a preference for dark matter, but very, very low. As we don't trust these candidates enough, we can just set limits agnostically when comparing to the embodied cosmological simulations. And these limits are improved a factor 4 with respect to no filtering at all, no spectral analysis done. And they are competitive with the CMB constrained by Planck and the dwarf spheroidals. Rebecca also mentioned here, we are off a factor 4 or 5, but we are competitive, and most importantly, they are completely independent probes for dark matter detection. And finally, I would like to talk a bit about spatial analysis, because in the last years, there have been some claims that brightest dark matter subhalos should be spatially extended. They call it a smoking gun for annihilation dark matter. When we
5 minutes, Javier.
Thank you. When we go to our simulation, again, we have the J factor, but now instead of the distance to the Earth, we have the angular scale when iterating up to the scale radius, which is a measurement, very usually in embodied cosmological simulations. We see that many of these subhalos, the brightest subhalos, exhibit very large angular scales, order 5-10 degrees, okay? Regardless of the mass. There is no trend in the color, actually. And due to the point spread function, as Rebecca mentioned, an extended source can be seen as point-like. Anything below here, even if it's, for example, at, I will go here, at 10 GeV, at 1 GeV, which is the green line, anything below cannot be distinguished from a point source. If you go to 10 GeV, everything can be resolved. So it's also dependent with the energy. So we can ask ourselves if any of our candidates is extended. The answer is no. We can do a similar log likelihood ratio test of the extended model versus the point model, and everything is monotonically decreasing. So everything is point-like, completely point-like. And this is just to have another example. This is an extended unidentified source, which is not fitted to dark matter, but as you see here, there is clearly a rise in the likelihood pointing out to some extension, but we are not seeing this. Nevertheless, we cannot discard any source just for this reason, because we have some work in progress actually to fully understand the sensitivity to extended subhalos. These are preliminary results, but when we perform some simulations with actual spatial profiles coming from this clumpy software and the envoy simulations, we obtain this picture. So the flags required to detect an extended subhalo, which would be the green squares here, is roughly a factor 2 larger than the point source case. Okay, this is what I showed before. And we have now this is slightly above. This is the ratio here, so a factor 2 more or less. But if we want to have an equivocal extension, so TS of extension 25, a 5 sigma preference for extension, we would require a flux 10 times larger. So we are talking about some very, very large fluxes here. Likewise, thank you. Likewise, I'm finishing. Likewise, the relation between the extension and detection significance is very linear, meaning that the brighter the source is, the most likely is you detect an extension if it's extended actually. And above, this is highly dependent on the mass. Basically above 200, 500 GeV, the Fermi lat is not a good instrument for extended dark matter, which is something we already knew actually due to the energy range. And finally, we can detect the angular extension of the subhalo depending on some parameters, for example, depending on the annihilation channel. And the point here is that even if the preference is very small, we are always detecting something. This is not zero, never. It's 0.1, 0.2, 0.3, but we should detect some angular extension. So even if these are preliminary results, in principle, we should detect actually the subhalos as extended sources, and if not, they are not subhalos. This is the preliminary results, and they could be used as an additional filter, of course, to refine the constraints. And I will just leave here the summary to not go over time. Thank you very much again, and of course, I'd be happy to take any questions. Thank you.
Thank you, Javier. Very nice. We have time for 2 quick questions. If you have any question, please raise your hand. While people decide, I have a quick one actually. You mentioned that halos could be as small as 10 to the minus 12, I think.
Yes.
How would they survive tidal forces?
Yes, actually, this is a very hot topic in the field. It's a very good question. The most realistic answer I can give you is no one knows, because we don't know actually if these so small subhalos exist. In principle, they could survive, but if they are very close to the galactic center, it's very difficult that they survive. Nevertheless, there are some simulations out there. There are some papers by Frank van den Bosch and Go Ogille, which point that there is no tidal disruption actually in these low mass subhalos, because they are extremely concentrated, meaning that these low mass subhalos, they have already been tidally disrupted in the past. They have lost most of the mass. That's why they are so small, and they are extremely concentrated objects, and no tidal force can disrupt them.
Interesting, thank you. Unfortunately, we don't have time for more questions, and I don't see any hands being raised. As usual, we have the Slack channel if you have any late question. So thank you again, Javier. Let's go to the next speaker, Maria Angeles Perez. Whenever you're ready, you can share your screen.
Okay, thank you.
Okay.
Can you see it
yes.
now?
Yes, thank you.
Okay. Very good. Thank you very much for this nice series of talks today about indirect searches. So I'm going to present a work and that we have been doing about the thermal history of neutron stars mixed with self-annihilating light dark matter. So this is done in collaboration with Hovik Grigorian in the GINR Russia, Conrado Albertus, David Barba at the University of Salamanca, and Joe Silk at the Institute of Astrophysics in Paris. So let me just introduce a little bit the basic concepts on neutron stars. So as Rebecca was saying in her nice talk before, I'm going to concentrate of the consequences of having dark matter captured in a type of astrophysical body that is a neutron star. So basically a neutron star is has a structure consisting of a core and a crust. So the core is essentially 10 kilometers or a little bit more, made of very dense astrophysical matter, neutron-rich matter, consisting of nucleons, plus a lepton sector, which is typically electrons or muons. And on top of that, there is a crust, which can be also separated into two phases, an inner crust and an outer crust, where matter is no longer uniform, spatially uniform, but is sort of consists of sort of nuclei, and matter is much more light. So typically these objects are described using macroscopic properties, masses and radii that can be measured, or better said, they can be constrained. So on the right, you can see a picture that shows some of the constraints that are typical for these objects. So you can see that constraints from electromagnetic radiation. This yellow region here comes from NICER, American mission attached to the ISS, that tell us that essentially neutron stars should have a radius which is not much larger than 14, 15 kilometers. Also, there are some constraints coming from measuring directly the mass of the object, which essentially is putting some pressure on having a description for the interior, that is the equation of a state capable of obtaining objects of two solar masses. And also there are some constraints coming from gravitational waves, essentially mergers of neutron stars, as tell us that the radius should be in this region. So these objects are essentially compact and very dense, and they can be very efficient at trapping dark matter. So what we have considered is what is the typical cooling behavior of these objects. So if one follows the classical theory of cooling into in general relativity, you essentially have to solve these two equations, 1 and 2, shown here, where essentially you have a description consisting of having the temperature variation with time, depending on essentially the luminosity that is present in the object and the ways of cooling. So here you can see on the right, this Q is describing the emissivity, so the kind of reactions that you can have happening inside the star that are cooling the star. So this is essentially well known or quite well known from standard model physics. They essentially involve cooling by neutrinos first, in the 10 to the 5 years, and then cooling by photons. And there is the possibility of having some heating that is energy injection in the object. So with these characteristic parameters, you can essentially model what is happening inside the star. So there are other properties. You can see here the CV, which is the heat capacity, And this kappa here in equation 2, which is the thermal conductivity, which is also telling us which are the degrees of freedom that you have in the interior of the star. Typically, for neutron star, you consider that there are nucleon degrees of freedom. There can be other exotics like hyperons or even quark matter, but we are not going to consider those at this in this work. So one interesting thing is see that the emissivities and the heating terms here come with different signs. So essentially, while the emissivities, the standard model emissivities, cool the star, the heating terms essentially inject energy. You can also see that there are these phi functions and lambda functions coming from the fact that we have curved space, and we can no longer consider a flat space. We have some metric, so this is explained here. But essentially, the main physical ingredients are given by these 4 parameters I just talked about. So our assumption in this work will be that what about these heating terms coming from dark matter self-annihilation? So why this? So this idea comes naturally if we think that, as explained before, that dark matter can be accreted very efficiently. So you have this gravitationally focusing onto the very compact star. The gravitational redshift is very big, is essentially about 0.1. Many orders of magnitude much larger than for the sun, for example. And while the dark matter enters inside the star, essentially if the cross-section scattering with nucleons is larger than a critical value that can be estimated to be 10 to the minus 46 centimeters square, dark matter can be gathered at the center, at the very center of the core, and then reactions can happen. So we are going to focus on the possibility that dark matter self-annihilates and finally gives some neutrinos in the final state. So in principle, we are going to focus in this particular calculation we have done on light dark matter models. So for light dark matter, I mean below 1 GeV. So essentially, if we go to, for example, results from CDEX, we see that for masses of about 0.1 GeV, typical constraints based on the Migdal effect are the 10 to the minus 33 centimeters square level. So we are very safe that our star can be opaque or present a large opacity towards this light dark matter. So in particular, we are going to focus on the self-annihilating model that we studied before based on some pseudoscalar mediators. So dark matter self-annihilates, changes mediator, and then you can have either final a pair of fermions in the final state, or you can produce some of these pseudoscalar mediators, and then they can subsequently decay to a pair of neutrinos. So essentially, they are coming from this interaction Lagrange. So the key parameter to consider here is just emissivity, as I said. So the emissivity has this particular form regarding the interaction that we consider. In this particular case, as I said, I'm going to focus on this, but could be done for any other kind of interaction that you like. You have to integrate over the square matrix element times form factor, a phase factor, which is essentially given by how your dark matter distributes inside the neutron star and what are the final states. So for the dark matter, we are going to use a typical Maxwell-Boltzmann distribution. And for the neutrinos, we are going to consider that they no longer stay in the star, but when they are produced, essentially they diffuse out and they are released. So the number of light dark matter particles inside can be approximated by a number which is solved by just considering this ordinary differential equation, where the most important part is just the rate of variation of this number. We are going to focus on a simplified model, just considering capture and annihilation. Could be also very interesting to include other factors, but we have not done that in our work. So capture has been estimated by a number of people in the 70s and 80s, and has this particular form, which belongs, of course, on how big is the object, the mass and the radius of the object, what is the mass of the dark matter particle that you capture, and what is the typical ambient dark matter density that you have. We have put here a solar neighborhood value, but essentially dark matter should be considered at the site where the neutron star resides. So typically in our galaxy, the peak of the distribution of neutron star is essentially about a few kiloparsecs. So it could be much, much higher than this value. So for the self-annihilation rate, we are going to consider just this figure, 10 to the minus 26 centimeter cube per second. And this annihilation rate has to be considered in the actual site where annihilation takes place. And this is the inner core of the star where dark matter is sitting. So for this inner dark matter core, one can estimate what is the typical radius, and considering just a few numbers of what is the typical temperature at the beginning or at the nascent hot neutron-rich neutron star, you can just put an estimate of 0.1 MeV. Typical nuclear density of about 2 times saturation density. So that's 2 times the density of a regular nuclei on Earth, which is typical for a neutron star. Could be higher, but this is typical. So essentially you have the dark matter is sitting in the inner kilometer, 0.8, about 1 kilometer. So with these numbers, one can estimate then the annihilation rate, and then you obtain this number here.
Excuse me, Maria Angeles, can you
Yes,
do it in presentation mode to maximize the size of the screen?
Yes. Can you see it better now?
Yes.
Yes, okay, thank you. So for the emissivity or the impact of dark matter, we rely, as I said, on the interaction Lagrangian that we obtained. And if we calculate that integral, as I told you before, you end up with this this parametrization, which is very very simple. And you can see here in this plot. This is taken from previous work, as I said, and you can see that for models A, B, and C, which just consider the different masses for the particle dark matter, you have this trend here. While for a standard model physics, that is typically no consideration of dark matter at all, you can see that the tendency is this black line here, very different. So these processes are I'm not going to enter into detail because they are very complex, but these are referred to as modified Urca processes, and they have this tendency for typical densities that we consider of T to the 8, while the dark matter emissivity is goes like T to the minus 3. Okay. You can see, however, that the exponent here is similar. So depending on the parametrization that you consider, depending on the value of the dark matter mass, you can have that either this alpha here goes from 19 to 21. So it is reasonable to think that there would be some competing effects coming from these two processes. We are going to consider also the fact that this light dark matter could contribute to conduction. So this is not new. This is an idea that was first explored in the sun by Spergel and collaborators in the 70s, I think. And we are going to consider this conductivity can be due to standard model particles, which are nucleons, electrons in the star, plus a contribution from dark matter. So this contribution can be parameterized just as the typical velocity, mean free path of dark matter times the particle, the dark matter particle number. So for the velocity, we just consider that this essentially thermalized, locally thermalized. For the mean free path, one can estimate naively this number times, so this the inverse of the cross section with nucleons times the density of nucleons. But effectively, this number will be, since the dark matter is a massive particle, it's not like a neutrino, a massless neutrino, it will be effectively just a few times the radius of the dark matter core. So when we
5 minutes,
obtain,
Maria Ángeles.
yes.
5 minutes.
Okay. So when we put all those ingredients in our code and we solve the differential equations, we obtain something like this. So this is a result for 0.1 GeV dark matter mass. You can see here that we have considered different values of the neutron star. This is, sorry, I didn't tell you, this axis is just the logarithm of the surface temperature, the redshifted surface temperature in the star versus the logarithm of the time in years. So all the stars here 10 to the 6 and very, very young, just born stars over here. And you can see also some experimental measurements for series of pulsars, some of them famous probably for you, Crab, Vela, and Geminga. So the solid line here depicts the effect of having the dark matter of 0.1 GeV included in our calculation. And the dotted line here, the dashed lines, those that are not solid, do not include dark matter at all. So you can see that the main effect is for temporarily to halt, to stop the decrease of the temperature. So in this region, depending of course on the mass of the object, could be from 1 solar mass to 1.9 solar masses. So the star, when dark matter and the modified Urca processes, the temperature is small enough, depending on the mass, you can see that it sits on a different region. It will be able to compete for quite some time, and then it will decrease, okay? Because you must remember that dark matter can only compete directly in the inner core. Outside the inner core, there is just standard model matter, and the star will cool off. So we have considered here the effect of enhancing the dark matter emissivity by just a factor of 5. And you can see that when you do that, the star essentially can have like two, you can see them here, two plateaus, okay? So you can have this competition here for quite some time. So the temperature is shifted upwards, okay? If I compare this to the previous, for the same masses, for example, 1.5, we could see that this plateau here sits at a lower temperature that's sitting here, okay? And again, essentially, when the emissivity, as I said, considering dark matter is larger, the star can compete a little bit more. So one interesting thing to see here is that, for example, for some group of measurements, you can see here this group of measurements, considering these two pulsars and the Geminga pulsar, they all essentially can be combined into into the same cooling curve, this pink 1.5 solid curve. While if I consider this other scenario, they belong to different masses. Okay, so you can see here that this belongs to essentially 1.42, while this belongs to 1 solar mass. They do not belong to the same cooling core. Okay, so just a conclusion, we have considered neutron stars are mixed with self-annihilating light dark matter that may temporarily halt the cooling in the context of enhanced emissivities for the dark matter model studied. Of course, this is just the model that we studied. It could be that for other models that they do not produce such enhanced emissivities, this effect is not present. The cooling history we have found that can be greatly affected with the presence of one or more plateaus, shifting them towards higher temperatures and larger duration for enhanced emissivities. Degeneracies in neutron star masses and age must be resolved, as I told you, for they belong or not to the same cooling curve. And complementary constraints on individual masses may help resolve the true cooling path. Okay, so thank you very much.
Thank you, Maria Angeles. Thank you. Very nice talk. Sorry, I was muted. We have time for one quick question if there is anybody that wants to ask. Raises the hand. Otherwise, thank you, Maria Angeles, again. In Slack channel anytime. Now let's move to the next speaker, Cosmin Ilya. Share the screen whenever you can, please. I don't see anything. It says you're sharing the screen, but I don't see anything. You are muted also, Cosmin. I still don't see anything. Maybe you can unmute your microphone.
Yeah, sorry, some technical difficulties. 1 second, can you all hear me now?
Yeah, now we can hear you. Thanks.
Yeah, I was living with a spinning beach blue ball of Mac, unfortunately, for the past minute or so. But there we go. And hopefully I can share my screen as well.
Now it
right,
works.
Finally,
thanks.
Back on track. You guys see my screen?
Yes, thank you.
All right, sorry for the little bit of a hiccup there, but I guess part of Zoom conferences, you know, by now we learn to love them and hate them at the same time, right? And part of it is technical internet difficulties. Anyhow, I want to start by thanking the organizers for this opportunity to talk to you all a little bit about some recent work. And the two papers that I'm going to summarize to some degree today are mentioned here. Basically, at the very least, my hope is that by the end of the talk, I will make you curious enough to scan those or put in the ID numbers on archives and look at the papers in some more detail. And the most optimistic scenario, I would have convinced you all, or some of you at least, that population 3 stars, or the first stars in the universe, are really good candidates as dark matter probes or laboratories, all right? Now, this work has been done as a collaborative work with current or former students of mine at Colgate University. Caleb Levi, who's still a student, and then Jacob Pilawa and Sayan Zhang, both of them grad students now. Moving on, basically, Rebecca mentioned in her nice talk towards the end of it that part of indirect detection methods are these indications that effects of dark matter annihilations or decay inside compact astrophysical probes could be very soon observable with instruments, right? So for this reason, this topic is becoming relatively hot in the literature, with hopes that soon enough, this heating effect, if you will, is going to be observed with infrared telescopes, okay? And such objects were considered even in the past, in the 80s or so, the Earth and the Sun, by prominent people that developed this field, such as Gould and others, right? Now, what I want to talk about today is this little corner, if you want, of parameter space, the first stars. And so let's start with this. I gotta give you a little bit of a bird's eye view, if you want, on what the first stars are and why they're interesting as dark matter probes, okay? So on the left panel here, there's a picture from a very nice paper of Brom, 2009, where simulations of first stars formations have been performed, results reported, and on the 4 panels, you see at different scales what will become a star, a first star. First, we have a cosmological halo. Then the simulations of n-body hydrodynamical simulations, let's evolve dark matter in conjunction with baryons. The baryons are going to gravitationally collapse towards the core, eventually forming here what's called a fully molecular core, which will become then a protostar, okay? And eventually a first star or population tree star. Now, those objects form at really high redshifts, where naturally the dark matter ambient densities themselves are high, right? So for this reason, compared, say, with our galaxy, the dark matter densities at such high redshifts, even the ambient ones, like the average ones, are much higher by a factor of z cubed. However, as I'm going to show you in a few slides, this gets even further enhanced by the collapse of baryons themselves, right? The other reason they're interesting, besides the dark matter densities being high, is that they form usually in isolations with few companions. Now, one of the challenges of indirect dark matter detection methods is that the objects considered usually live in ambient media, where it's kind of hard to extract if you want the signal, because the center of the galaxy, which is one of the most well-studied such environment, well, it's full of quote unquote, if you want, noise, right? So there's so many other things that maybe some of them we do understand, maybe we don't, but there's many, many other things besides, say, for example, the neutron stars we're looking for, right? Now, in the case of population tree stars, they would form roughly 1 or so per halo. So taking the signal out of the noise, it's very easy, if you will. Now, the other reason they're important or relevant is because they're very massive. They're expected to grow to masses up to maybe 1,000 ultra-solar masses, okay? Now, something I will not tackle at all today, so maybe I should just skip this part. I will just skip that part, okay. Let's see what's the observational status, because those objects are hypothetical. They have been seen in simulations, but were they yet observed or not? That's the question. And actually, it's an actual valid question because it seems that they might have been observed even with the Hubble Space Telescope. There is such a candidate population 3-star complex described in this paper by Vanzella and collaborators, at redshift roughly 6.6, if you want, that has been identified. And obviously, follow-up observations with the Webb telescope are going to be important in determining if indeed this target is a complex of population 3 stars. No matter what, this excess Lyman alpha flux is very well describable with a population of pop 3 stars with masses of up to 1,000 solar masses or 300, depending on however many there are in this complex here in the Muse deep lens field. The prospects are good, actually, and it's timely because the James Webb Space Telescope is one of its primary missions is to observe the first light or the first stars. And also we have this actual successor of the Hubble telescope, the Roman, or previously the W1 telescope, which is still a good infrared telescope with which we can see deep in space, which is relevant for population 3 stars formation. Now, I come back to this idea of dark matter densities. Are they high enough, or how high are they? So let me start on the right side. We're going to read this slide from right to left, right? On the right side, we have schematically what's happening when I have this pristine collapsing gas cloud. It collapses close to the center of the dark matter halo. And as any respectable physicist, I choose a spherical cow, right? Obviously, my cloud is spherical because it's simpler to do it that way. Maybe there's going to be some anisotropies in it, but anyhow, this gas cloud is collapsing under gravity. And dark matter orbits will respond. They have to respond, okay? Just because of the enhanced potential if you enter the center. And this response of the dark matter orbits is what's called adiabatic compression or adiabatic contraction. And there's a very simple formula in the literature. The simplest of all is the Blumenfeld formula, which basically says, well, I can consider adiabatic invariance. And the simplest one is conservation of angular momentum in the dark matter orbits. If I assume such conservation, one can actually compute what is the dark matter density for any given baryonic density of this cloud. And this is done here on the right, on the left panel. Or say, for example, we start with a standard NFW profile and evolve it for different densities of this baryonic cloud, starting, say, with 10 to the 9, all the way to 10 to the 15. So the various lines are like so. This corresponds for the 10 to the 9 up to 10 to the 15th baryonic density during this collapse, okay? And what you notice is that certainly we have enhancement orders of magnitude above the standard NFW profile. Now, what's also remarkable about this picture is that simulations do confirm it. So you see, in 2002, Abel has done a cosmological hydrodynamical simulation, the formation of first stars, and the response of the dark matter profile is plotted with the stars here. And you see, up to the resolution limit of that simulation, the stars really do follow a trend of adiabatic compression. Now, I will talk a little bit about dark matter capture very schematically for now, and tell you that essentially, as a dark matter particle crosses any astrophysical object, obviously it will collide with constituents inside that object. For us, population 3 stars, they're mostly hydrogen dominated. So those green points here are just, say, protons, okay? Via those collisions, there will be energy exchange. The red dot, the dark matter particle, would lose energy, and eventually it could become gravitationally trapped, okay? So say it collided enough times that it becomes gravitationally trapped, then eventually they would all sink towards the core, and they would form actually a dark matter core. Dense enough that dark matter annihilations would be significant. We would have effects of those dark matter annihilations, such as standard model particles, light and secondary particles, and overall, unless you have a lot of neutrinos, most of those particles are going to thermalize within the star, leading to an object that shines brighter. And here comes really the key of our method. The key of our method is that there's a limit to how bright any object can shine. And that limit is called the Eddington limit, okay? So for example, in this plot right here, all we're doing is to say the following. This object, any object, and the objects we're considering here are 2 population 3 stars, one with a mass of 100 solar masses and one with a mass of 1,000 solar masses, is Eddington limited, all right? So this statement alone can be recast into a bound of combinations of dark matter particles, dark matter particle parameters, or dark matter parameters actually, of which the relevant ones are the dark matter density, rho chi, sigma, the scattering cross-section, and the mass of the particle itself. So you see, right now, just assuming we observed those objects with a different masses, we can place bounds, upper bounds, on this combination of dark matter parameters, dark matter density times sigma. That's a very strong statement. However, typically, what one is chasing is one of the two, either sigma or rho chi, okay? So say, for example, if direct detection experiments pin down what the cross-section is of interactions between protons and dark matter, then immediately we can recast this into bounds of the dark matter densities at the center of halos where first stars form. And that, to my knowledge, is the only way I know of constraining that parameter. Because dynamically, I don't think there's any instrument that we can conceive of at this stage that could actually probe those dark matter densities. So we have two ways, either simulations, or hopefully if we can pin down sigma and observe some population tree stars, then we can constrain this parameter. But in this talk, I'm going to take the other approach. In this talk, I'm going to say, okay, what if we assume, based on adiabatic contraction, that there's a range, there's an uncertain range of dark matter densities, obviously, and we motivate it in the papers. If you're interested to see the motivation, we can talk later or in the papers. Ranges say from 10 to the 13 to 10 to the 16th GeV per centimeter cube. That is many, many, many orders of magnitude higher than the local dark matter densities, or even the dark matter densities at the center of the galaxy. So for this reason, if now we break the degeneracy and we place bounds on this cross section, there's two things that we notice. First of all, the bounds are the bounds which are basically now shaded regions, right? Those shaded regions correspond to the limits, right? And there's a band or a broad stroke I'm painting with, just because the density is not fixed. So this broad stroke of my brush corresponds to the width of the density I'm considering, dark matter density, okay? The other thing I want to point out is that the objects give the same bounds for spin-independent and spin-dependent interactions. And now I'm contrasting on the left versus, say, the most powerful experiment currently to constrain spin-dependent dark matter, Pico 60, and even the neutrino floor relevant for that experiment. And you see, even a 300 floor mass POP3 star is able to constrain below this neutrino floor for spin-dependent experiments. Conversely, for the spin-independent case, our constraining power is on par with Xenon 1T, not much deeper. But still, the region of parameter space explored here is above 1 GeV. So right now, I'm still only focusing on dark matter particles with masses above 1 GeV. As you can imagine, you can extrapolate this to lower, and yes, evaporation would do something, but still the region below 1 GeV is really interesting. And if I have time, I would come back to it later in the talk, okay? But for now, basically, the key takeaway is that assuming the observation of POP3 stars of masses higher than 300 solar masses in the near future, or the ones is observed by Hubble in Vanzella's candidate system, implies really deep constraints on this parameter, on the cross-section of interaction. The other thing I want to point out here is that the higher the mass, the deeper we probe, okay? In other words, the objects that are more immediately observable, the higher mass, that means this object is going to be easier to observe, is a better probe for dark matter parameters. And that actually is in stark contrast.
There's 4 minutes left.
4 minutes, thank you. That actually is in stark contrast with, say, for example, neutron stars or other probes that have the parameter that's measurable, temperature. In that case, the lower temperature ones, in other words, the ones that are most difficult to detect, are better probes. Okay, so that's one of the reasons I think POP3 stars are good candidates. Now, certainly one could point out, well, yeah, you have quite a huge range here of dark matter densities, do we even know that's the case? The answer is, unless we have a simulation that probes so far deep in the dark matter mini halos where pop-3 stars form, there's no real way to know when this adiabatic contraction formless stops. So those values should be taken with some grain of salt, right? But I also want to point out, as Rebecca did earlier, that even for our galaxy, we don't really know exactly the profiles of the dark matter density in the inner parsec or so, kiloparsec or so. So that ambiguity persists both for indirect detection experiments within our galaxy and to another degree for the method I'm presenting here. Now, very briefly, I want to kind of give you some details of how we extract those parameters, right? So the plots we've seen before, but now I'm just taking, okay, we need the nuclear luminosity. How do we get that? Well, we get it from simulations with, say, for example, mesostellar evolution codes, right? And those dots are for a given mass of the star, the luminosity in basically by hydrogen fusion at the core, okay? And we can have an interpolating line, and as expecting, this interpolation goes to almost linear at high masses. That's an expected finding. High mass stars shine almost at the Eddington limit, okay? Now let's move on to the Eddington limit. Well, the Eddington limit is a linear mass quantity, right? And plotted here. This parameter is the opacity of the atmosphere of the star in question. And then the other thing that we want to look at is the dark matter density, the dark matter luminosity for a given set of parameters. And in this case, we just chose a fiducial set of parameters with the mass of the dark matter particle 10 to the 4 GeVs. And we got this sort of evolution with mass of the star for the dark matter luminosity, okay?
1 minute.
1 minute, all right. Then I'm gonna very quickly go to what happens at below the GeV mass. So I'm gonna, let me not make you guys dizzy. Let me just go very quickly here in 1 minute. How about sub-GeV? Well, the model we consider is this co-SIM dark matter model introduced by Smirnov and Bicorn in 2020. And we asked the same question, can we constrain this interactions with protons of this model? And the answer is yes. And essentially by doing exactly what I've done before, but now including the effects of dark matter evaporation, which we can see in these scoop-like regions here, we're constraining both the spin-dependent and spin-independent. So I have a spin-dependent here and spin-independent on the right side. Cross sections, and contrasted are discovery limit, or in other words, the neutrino floor, and the most up-to-date we found direct detection experiments. And as you can see, those objects, even for the lowest case of the density we consider, 10 to the 13, are still really good probes of cross sections of dark matter. So in summary, I have shown that pop-3 stars can be powerful probes of dark matter. Now, if we assume a dark matter density, which we've done here, we can place bounds on dark matter proton cross sections. And conversely, if direct detection experiments help us to pin down sigma, we can constrain the densities in the ambient environments for pop-3 stars, right? And for sub-GeV dark matter, we actually found that they're really, really, really good probes of such interaction cross sections between dark matter and protons. And because I'm almost out of time, I would stop here and thank you all for your attention.
Thank you, Cosmin. Very interesting. We have time for a very, very quick question. Meanwhile, while we wait,
I'd be happy to take questions in Slack as well.
Sure. I just wanted to comment, there was this prediction by Roger Windhorst, saying that there was a good chance to see individual pop-3 stars thanks to gravitational lensing.
Mm-hmm.
Yeah. All right, I don't see questions here, so any question can be done in the Slack. Thank you again.
Thank you.
So the last speaker of the session is Nimal. You can share the screen whenever you're ready.
So, hi, you can hear me, right?
Yes. We need
Okay, and you
full
can see
screen.
you can see my screen.
Yes.
Okay, very good.
Right.
Sorry, give me 1 second. Let me try to move the tab up here. Okay, good. So thanks everyone for being here, and thanks a lot to the organizers for having me and for putting together this wonderful workshop. So I wanted to talk about, sorry, my voice is gone this morning. So I wanted to talk about some fun ideas I've been exploring with David McKean at Triumph and Maxime Pospolo at Minnesota. And in this talk, I'm going to be exploring a hypothetical new particle characterized by its neutrality under all known fundamental forces, its spin, which is 1/2, and its baryon number, which is 1. Now, if I put it that way, the disapproving ghost of James Chadwick is going to object, saying that what I've described now is nothing but the neutron, right? And that's kind of the point, because what I'm describing is what I would call a dark neutron, where the dark signifies the fact that we haven't detected it so far. It's hidden from our searches. And the difference between the dark neutron and the neutron is that while we know the mass of the neutron, which we've measured very well, we don't really know what the mass of the dark neutron is. So that the two-state Hamiltonian of the neutron and the dark neutron in vacuum would be given by this matrix on the right, where I have the diagonal masses, Mn and M chi, but I also have an off-diagonal mass that I'm going to call epsilon n chi, which you cannot forbid, so that gives rise to quantum mixing. Okay, and that quantum mixing is going to give rise to all the phenomenological effects that we're going to see today. Good. Now, why do you care if there are dark neutrons around in nature? Well, this is a dark matter workshop, and dark neutrons could very well form the dark matter of the universe if they are sufficiently long-lived, cosmologically long-lived. Okay, and we'll see about this idea in a bit. And then there's also the neutron lifetime puzzle. I hope you can see this animation. This is an experimental anomaly that's been observed over almost 3 decades now. Basically, neutrons seem to disappear faster from bottles, such as ultra-cold neutron facilities, than the speed at which the decay products appear in neutron beams, for example. Okay, and this discrepancy has been measured over many years, and today it stands at a 4.4 sigma discrepancy at the level of a percentage, at the fractional level of a percentage between the rates at which you measure the decay process in these two methods. And where do dark neutrons come in this picture? So as Bart Fornal and Benjamin Greenstein showed us in 2018, this discrepancy could be explained by a 1% branching of the neutron to a dark neutron plus anything else in bottle facilities. But you could also get this by having a 1% probability of the neutron resonantly oscillating to a dark neutron in a beam, as shown by Zurab Bereziani. Okay. And then there's also dark neutrons could also feature in the xenon one-ton excess that was observed last summer. Basically, some anomalous electron recoil events seen at small keV energies in the xenon one-ton experiment in Gran Sasso. And Dave, Maxime, and I showed that one possible explanation could be dark neutrons produced by electron capture on protons in the hydrosphere of the Earth or in the sun, that could, with various mechanisms, deposit the right amount of energy in the xenon 110 detector with the right amount of flux to ease the tension that is seen at these low energies. And something I'm not going to discuss in this talk is dark neutrons also play a ubiquitous role in the baryon asymmetry of the universe. There's a lot of literature on that I've listed on the right here. Now, the concrete realization that I'm going to be talking about today is this particular model of dark neutrons, where at the hadron level, the Lagrangian could be described by, the relevant Lagrangian could be described by this mass mixing term on the left. And that mass mixing would give rise to an effective transition dipole of the neutron to a dark neutron, which I've written down here, characterized by a mixing angle, which is given by nothing but this mass mixing divided by the difference in masses for small mass differences. And the strength is, of course, given by that mixing angle times the neutron magnetic moment. Now, because of this transition dipole, you could have neutrons decaying to dark neutrons and spitting out a photon and vice versa, depending on which is kinematically open. As shown on this in this diagram on the right. This diagram also gives you a UV completion of this model involving integrating out a heavy diequark, right? So now you have a prediction for what the decay rate of the neutron to the dark neutron is. What you find is that to explain the neutron lifetime puzzle, you would roughly need a mixing angle of around 10 to the minus 10 and mass splittings of around 10 MeV. Okay, and you could also write down the decay rates of the dark neutron going to the neutron and the dark neutron decaying to proton, electron, and neutrino whenever kinematically available. Now, if you want to do cosmology with dark neutrons, you want to know how many of them were around in the early universe. And in particular, you want to see if these interesting cases where the dark neutron population matches the visible baryon populations so that it could probably be a viable candidate for dark matter. You want to check if that's possible, or you also want to check if other interesting phenomenology is possible with smaller amounts of dark neutrons. And you can turn the crank and you see that to actually do this, to see if you are in chemical equilibrium, you find that you're actually above the QCD transition, so that you need a quark level description of the number changing process. And what you find is that you can keep chemical equilibrium when the universe was all the way down to a temperature of GeV to a PeV for the mixing angles and mass splittings that we're interested in. And that means it's not unreasonable that the dark neutron population was comparable to the visible baryon population, because the universe was probably that hot, at least at GeV. Okay, so where do we find these fantastic beasts? Well, one place you could look for them is when the universe was shaped by neutrons and protons and electrons, namely Big Bang nucleosynthesis. So here is the reaction network for Big Bang nucleosynthesis. But here I've also added the role of a dark neutron. It could interchange with a neutron via this transition dipole. And the idea here is that the presence of the dark neutron would basically, because it can repopulate neutrons, it can basically mess up with the timing of the freeze out, the neutron proton freeze out. And that would show up as modified abundances of helium and deuterium, which I'm showing on the plot on the right as well. The plot on the right basically shows abundances as a function of time or inverse temperature. For various mass splittings and couplings, you get various effects because of primarily coming from the timing of the freeze. You could also look for dark neutrons in the power spectra measured in the cosmic microwave background. Here is a famous cartoon of the timeline of the universe. And here is the CMB as the fourth oval from the left. So just to the right of the CMB is the dark ages. And if the dark neutron is sufficiently long-lived, if it outlasts the recombination epoch, and if you have these channels kinematically open, that is, if you have the dark neutron decaying to protons and electrons or to the neutron and the photon, then the resultant electron or photon would dump energy in the dark ages and rewrite the reionization history, hence modify the optical depth and mess up with the measurements of the temperature power spectrum. So that could be another testing ground for dark neutrons. And then we stumbled upon a novel mechanism to heat up neutron stars with dark neutrons, which gives you extensive coverage of dark neutron parameters. So when I say neutron star, the image that you probably have is a giant nucleus in the sky. It's probably a pulsar, as Rebecca was mentioning. But the other image that you probably also have is in energy space. The nucleons and the electrons as well are distributed in discrete energy levels. This is the Fermi sea of the nucleons, and the typical Fermi energy of neutrons is order 100 MeV. Now, if you have dark neutrons around in nature, then the neutrons via collisions with other nucleons and also via exotic decays could interconvert to dark neutrons. And when that happens in the Fermi sea, you create holes, right? And nature abhors holes, because when you create these holes, the neighboring nucleons would rush in to fill these holes immediately. And that would be inevitably accompanied by a spillage of energy. We already see this in atomic systems. This is known as the Auger effect in semiconductors and atomic systems, used to treat cancer and so on, but we could completely translate this to neutron stars as well. And given the fact that there are 10 power 57 neutrons and 10% of that is in the form of protons, you find that very quickly you will find that all this leads to an explosive liberation of energy in the neutron star and anomalously heats up neutron stars. So you could use this as a probe to set constraints on dark neutrons by using the coldest pulsar that's ever measured, which is around 40,000 Kelvin in temperature, which I'm highlighting here. Now, this could also be used as a future laboratory. A few years ago, with some amazing collaborators, I wrote this paper in a completely different context on dark matter ambient dark matter getting captured in neutron stars and heating neutron stars up to temperatures that can be detected by upcoming infrared telescopes, such as the James Webb Space Telescope. These are optimized for around 2000 Kelvin. So in the future, you could also use these telescopes to look for these anomalously hot neutron stars. Now, let me take this opportunity to very quickly point out or advertise a paper that came out just yesterday or maybe the day before with one of the organizers, Bradley Kavanaugh and Joseph Bramante, combining these two astronomical ideas, the coldest neutron star observed and future neutron star observations. Basically, this is to look for anomalously hot neutron stars getting heated up by subhalos, which was talked about just 2 talks ago. There's also a lot of other papers on this topic. I'm just highlighting a few down here. Okay, so putting all that together, here is a pretty busy plot of all the constraints. This is for the dark neutron lighter than the neutron, so that the neutron decay, direct decay of neutrons to dark neutrons is kinematically open. And this is for an abundance that is 5.4 times the baryon abundance, basically making the dark neutron, all of the dark matter observed in the universe. One thing to remember here is as you go down in this plot, you are going you are basically accessing longer lifetimes in this mixing angle versus mass plot. There are too many things going on here, but I put all the constraints that I talked about here. One thing I want to highlight here is that because of the new constraints from Big Bang nucleosynthesis, that in combination with direct searches for neutrons decaying to dark neutrons and the photon at UCN facilities leaves a small 100 keV window that explains that lies on the parameter space that explains the neutron lifetime puzzle. And that's a very nice window that UCN experimentalists could target in the next run of their experiment, which they're already working on by reducing their backgrounds and improving their thresholds. Now, a little bit more on the neutron star heating probe. So not only could you use the coldest neutron star to set constraints, what I'm showing here on this plot of the off-diagonal mass term versus surface neutron star temperature is that you could also use somewhat hotter neutron stars, somewhat younger neutron stars as well. In fact, you could even use the youngest confirmed neutron star, Cassiopeia A, which is 330 years old, to set these constraints. The younger you go, the advantage of using younger stars is that gives you a ceiling or a lower limit on this mixing parameter, because if the neutrons are converting too fast to dark neutrons, then this heating mechanism doesn't work anymore, especially if the neutrons get converted within the lifetime of the star, then you don't have heating going on currently. So younger stars help you probe higher mixing parameters. Now, how does that compare with terrestrial ultra cold neutron searches? Here's how they compare. So on the other y-axis here, I'm actually drawing exactly the same thing, except this is 1 over the epsilon n prime, also known as the oscillation time in this language. And the red region is exactly the region that's probed by neutron stars on the left, whereas all the various curves here are the limits on the oscillation time as a function of a hypothetical mirror magnetic field that they assume in these experiments. The key takeaway here is that not only can our probe give us somewhat stronger constraints, but also that the neutron star heating probe actually applies for mass splittings between the neutron and the dark neutron, all the way up to 10 MeV. Whereas the UCN searches are only applicable for extremely degenerate neutron dark neutrons, that is at the level of 10 to the minus 18 MeV, which comes from the Zeeman splitting from the Earth's magnetic field. Whereas our splitting comes from basically the neutron self-energy per baryon in the neutron star. So in that space, we could basically probe 19 orders of magnitude more parameter space than terrestrial experiments.
4 minutes.
How many minutes, sorry?
4 minutes.
Oh, okay, great, thank you. So this is basically my last slide. These are things that I'm working on currently. So because you have these oscillations, because you have this off-diagonal element, you could set up neutron oscillations to dark neutrons and vice versa. And hence you could think about neutrons shining through a wall kind of experiment that could probe new parts of parameter space. So well, the cartoon picture here is somebody's throwing a neutron or bowling a neutron in cricket parlance, which is going through a wall, and the batter could basically meet it on the other side as a neutron. So some of the ideas that we're working on right now are in these bottle experiments in the UCN facilities, the neutrons could basically ping against the walls of the bottle, and in one of those pings, the wall of the bottle would detect it as a dark neutron and let it through, so that you have disappearance of neutrons from these bottles. There are also some intense neutron beams planned for completely different purposes in a few underground labs in the world. Notably, there's this ISODAR experiment planned in the Yemi lab in Korea. And here again, these intense neutron beams could convert to dark neutrons in the shielding, and that could be detected at a neutron at some detector like Thea or Camland or something at some distance away underground. There's also a lot of constraints that you could already place on this by looking for anomalous neutron events in detectors like SNO in SNO lab. The source here is basically cosmic ray neutrons produced as secondaries in cosmic ray collisions with the atmosphere. And when these neutrons hit the ground, again, they could be detected as dark neutrons and go through the rock and be seen at SNO in large quantities. Okay, so that's my conclusion stage. I'll just leave it there and I'll be happy to take questions.
Thank you. Very nice talk. We have time for 1 or 2 questions. If you have a question, please raise your hand. Out of curiosity, in that famous experiment, the bottle versus the beam, the light of the neutron, what is the reason why? I mean, if this mechanism is at play, What is the reason that in the beam case, you have a longer lifetime?
Can you say, what is the reason why it has a longer lifetime? Oh, basically.
Yeah, if you look at the plot on the right, the neutron lifetime is longer in the beam method.
Right. So in this, the theoretical explanation of a neutron going to a dark neutron, the bottle experiment basically has a higher decay rate. That is what the beam measures is, you only count the number of protons coming out of the neutrons. So that is the actual beta decay rate. And then on top of that, you add this extra 1% branching. That is an exotic branch.
Right.
So that's why in the beam, you see a longer lifetime or a shorter decay width.
Okay, thanks. Any update on the, I see the latest in the bottle method is more recent. Any update on the beam case with the smaller error bars?
Actually, no, unfortunately. That is the latest one. There are some beam experiments that have been proposed, but yeah, they're yet to go online.
Cool.
In fact, there are a lot more bottle experiments that are proposed because it's easier to do that.
Yeah, neutrons in a bottle.
Exactly.
All right. Well, thanks again. I don't see any more questions, but if you have any questions that come to your mind later on, there's always the Slack channel. I would like to take the opportunity to thank all the speakers. Some of the talks are already on the Indico website. Some of them we will upload because there's been some technical issues, but I think we may have some of them in the mail. So hopefully they'll be available tomorrow. Enjoy your night, afternoon, wherever you are. And we'll see you tomorrow again. Take care.
Thanks, guys. Thanks, everyone. See you tomorrow.
Bye-bye. See you tomorrow.
Thanks, everyone. Bye-bye.